very good morning to everyone and welcome to second day of our national conference of Midnapur City College on current trends and future extensions of green chemistry organized by Department of Pure and Applied Science. Today also we will be enlightened by the lectures of our esteemed guests in technical session 4 and 5.
We are fortunate enough that Professor Amit Basak, INSA Senior Scientist, ISER Kolkata, and Professor Chittaranjan Sinha, Jadavpur University, will join us today. Due to some unavoidable circumstances, Professor Saurabh Chatterjee, NIT Rourkela, and Professor Y.S. Chaudhary, CSIR Lab, IMMT Bhubaneswar, cannot join us today. However, Professor Chatterjee agreed to deliver his speech through online mode.
Cute.
Now we would like to request Dr. Jagannath Pal sir to kindly chair the session.
Want to smash it? I want to smash it. Sir, smash it. Hello? Sir, smash it. Smash no. Smash it. Sir, smash it. Sir, audible, it is audible.
হ্যাঁ শোনা যাচ্ছে, আমার কথা শুনতে পাচ্ছ? আচ্ছা ঠিক আছে, সো ক্যান আই স্টার্ট? মাঝে মাঝে আটকে যাচ্ছে। এখন শোনা যাচ্ছে? ওকে ওকে ঠিক আছে। হ্যাঁ আমি শুনতে পাচ্ছি। ওকে, সো আই ক্যান স্টার্ট রাইট? whenever you tell you I will start.
Sir, just a minute. অ্যাকচুয়ালি স্যার অনলাইনে একটু অসুবিধা যাচ্ছে।
We would like to felicitate Sir through online mode.
Okay. Okay, thank you very much. Thank you very much. I accept that in an online mode. Thank you.
Now we would like to request Dr. Jagannath Pal Sir to kindly chair the session.
Good morning, sir. I would like to thank you, Professor Saurabh Chatterjee, to attend this seminar. And Professor Saurabh Chatterjee from NIT Rourkela is an associate professor. He completed master degree from University of Bardhaman and completed PhD from Indian Institute of Technology, Mumbai. And he has completed several postdoctoral fellow from University of Bonn, Germany, from University of Bonn, Germany, from he also CSIR pool scientist from IIT Bombay, and he joined NIT Rourkela at 2007 and till date, and he is now associate professor from associate professor. Oh, professor. Yeah, sorry. He is now professor, and his research field is most of the functionalization of ferrosinil and half sandwich molecular entities and understanding their redox biological and photophysical properties, design of metal cluster framework for binary transitions mental group synthesis. And I would like to Professor Saurabh Chatterjee to start his conversation. Thank you, sir.
So can I start? Yeah, okay, thank you, Professor Pal, for your introduction. I first of all let me thank the organizing team, especially Dr. Abhishek Ghosh and his team, and also the Mednipur City College for such a nice organization. I'm sorry to be online today because of some unexpected happening where the train got cancelled and I could not able to join you, but I definitely would like to join you in the next time whenever it's possible. So let me go directly to the to my talk. I will put the entire screen. I will share this entire screen. Today I will talk about. So can you able to see?
Yes, sir. We are able to
Yeah.
see.
So can you able to see
Yes,
the
sir.
slides moving?
Yes, yes.
Okay. Okay. So, so my today's talk would be mostly focusing on the topic I have put here in my slide, strategic functionalization of ferrocyanide scaffold using solvent-free solid-state synthesis to design a very novel compounds called ferrocinophanes. So I will discuss little bit on the ferrocinophanes and its interesting importance, and then probably we will be discussing some of our research on this particular important compound. Although your conference is on green chemistry, my only green chemistry part is on the solvent-free solid-state synthesis, and we have been doing this solid-state synthesis without using any solvent for the last 5-6 years, and that is the only green part we are doing for organometallic synthesis. And it is, I am glad to say that these solid-state synthetic methods have been initially introduced by one of your professor, Dr. Abhishek Ghosh, during his tenure at NIT Rourkela, when he was doing my doing PhD with my in my lab. And of course, I am thankful to Abhishek for this initiation. Now, if we try to understand the functionalization behavior of ferrocene chemistry, okay, so this slide shows, diverse understanding of ferrocene chemistry in our laboratory. We have been undergoing different types of ferrocene molecules which are applicable for sensor studies, bioimaging, solar cell devices, catalysis, and also recently to inhibit amyloidogenesis and cytotoxic studies. So as a whole, we have been trying to understand the functionalization behavior of ferrocene and how to use those functional material for different applications. Now, if I come to the very initial topic of how to functionalize ferrocyanide scaffold and what are the varieties, so let me go on with the very simple one, which we call monofunctionalization. And this monofunctionalization is very easily achieved, but then it depends upon this functionality, that you can use this functionality for different applications. For example, if you use a electron donating or a electron withdrawing substituent at this functionality, then what we achieve is a donor acceptor molecule, because the ferrocene part is actually a donating entity. So this particular picture shows the donating ability and the accepting ability. And if we can give a conjugated link, then of course we came up with a donor acceptor molecule, which are very interesting for photophysical behavior and also in solar cell studies. I go to the next functionality, which we call difunctionalization. And very specifically, if we tell this difunctionalization as 1 dash, because the first functionalization at 1 CP and the other functionalization is the other CP, so that is called 1 dash. And when we put the same functionalization at both the CP, we call them as symmetrical functionalization. Now, this particular symmetrical functionalization can also be achieved by 2:1 ratio reaction. And here is an example where we have been able to get difunctionalization, which is of course symmetrical because both the functionalization is same. But then what happens is that, you see, the ferrocene here acts as a donor, and all these are electron withdrawing substituents, which make it sense that now we have electron withdrawing from the two different areas, different directions. So these are also very important molecules, and we have been able to synthesize some of these molecules. However, I am not talking all these details today. There are another functionalization which we call unsymmetrical bifunctionalization. In this unsymmetrical bifunctionalization, the functionality at both the CPs are different. Okay. Now, these are the real challenge to synthesize these molecules, because usually whenever we try to synthesize unsymmetrical bifunctionalization molecule where the two functionality would be different, we end up with a symmetrical functionalization, not unsymmetrical. So that's a real challenge where we had to understand the synthetic methodology. We have to change the synthetic methodology to solid state synthesis, where we could able to get a selective synthesis so that we can achieve the unsymmetrical bifunctionalization behavior. Now, very important of this kind of unsymmetrical functionalization is that they give rise to a chiral molecule. And this chiral molecule, of course, are very important sometimes to achieve in asymmetric catalysis. However, we are not being able to get the asymmetric part, but we have been able to synthesize some of these unsymmetrical bifunctionalization molecule. Like, for example, one example is given here. You see the functionality here is a rhodamine, which is a fluorescent active molecule entity, whereas in the other part, the hydrazone moiety is actually a bioactive entity. So here we have been able to functionalize unsymmetrically with a fluorescent active and also bioactive entities. So similarly, what happens when we try to functionalize in an unsymmetrical manner, there are different types of possibilities which comes when we try to unsymmetrically functionalize. For example, it can rotate, so the functionality can rotate in this fashion or in this fashion, or sometimes they lead to some kind of interactions between the two chains. And we have been able to get similar type of multiferous architecture with these unsymmetrical bifunctionalization efforts recently in these journals. However, there are other difunctionalization possibilities where the functionalization can happen at the same CP. That means the same cyclopentadienyl moiety with 1,2 or 1,3 type of functionalization. And in this also, in these type of functionalization also, they give rise to a chiral molecule. Recently we have been able to get a 1,2 type of functionalization with one of the palladium incorporated ferrosinyl pincer type complex, and we have been able to make this molecule to act as a catalyst for different carbon-carbon coupling reactions. I am not talking in that direction as well. So I am talking about this 1,2. So this is actually 1 and this is the 2. So sometimes these were also called orthopalladation. So these are orthopalladations where one of the functionality would be palladium. So these are also called palladicycles molecules. So here we have synthesized this palladicycle molecule recently, and we have been using for catalysis. There are different types of palladicycles or orthopalladations where 1,2 functionalization happens. So this is one example, and another example is this one where this type of 1,2 substitution happens with this CP ring. Of course, these are not widely known because in this case, you see, these are bidentate orthopalladation, and one of them is the tridentate orthopalladation. And there are very few of them known. Recently, we have also been able to get one of those synthesized and use them for catalysis. Now another type of functionalization which I will be talking in this presentation is basically called ferrocyanophen, and it's a very interesting part of the ferrocyanide chemistry, because in this ferrocyanophen what we try to do is that we try to uh, join two parts of CP. So like this, you see, if you can if somebody is pulling from here and somebody from is pulling from this side, then we end up and we lock it here, and what we end up is a ferrocyanophen. But then there are variety of ferrocyanophanes depending upon the number of carbon atom which is bridged. So we call them as N-ferrocyanophen depending upon the number of bridging carbon. And this particular ferrocyanophen molecule are very interesting. I would go one by one and let you know what is the interesting facts about these ferrocyanophens. And I will also let you know that these are very recent developments I will be talking about. Like for example, if I try to explain you a little bit of N-ferrocyanophen, it's a bridged ferrocyan, okay, where the 2CP has been bridged. Now you see, this is an example of 3-ferrocyanophen, where you have 1, 2, and 3 carbons bridged between these 2 CPs. There can be different number of carbons, starting from 1 to 3 to 2 to 4, 5, and etc. There can be different heteroatoms. So accordingly, the ferrocyanophens can be named. If there are multi-bridged, that means this is one bridge, there can be other bridge, like here. If there is a multi-bridged, then those ferrocyanophens are named as M.N.O.P depending upon the carbon atom present at the multi-bridge ferrocyanophanes. So here is another, which is the multi-bridged ferrocyanophane. You see, this is the double-bridged ferrocyanophane, and this can be named as 3,3-ferrocyanophen or 3.3-ferrocyanophen, or sometimes you can name it like this, 3,1-3,33-ferrocyanophen, because there are 3 carbon atoms in both the bridge. There are other types of ferrocyanophanes, which is something like this, where 2 ferrocyanophanes are doubly bridged between them, and it is called 1,1-ferrocyanophen because there is 1 carbon involved. So when we know the ferrocyanophen, let me just go one by one with the simplest one. And of course, when we tell simplest one, it is not very simple to synthesize, and of course they are of very wonderful significance, I will tell you. Now you see, this is an example of 1-ferrocyanophen because the bridged between the CP ring contains 1 carbon or 1 heteroatom. Okay, till now the 1 carbon ferrocyanophen has not been synthesized. The reason behind is that if there is 1 carbon, then the CP ring tilts so much that it destabilizes the whole moiety. However, if there is other heteroatom which is bridged, for example oxygen or sulfur or silicon or germanium or sometimes phosphorus, they are tilt in a lesser manner, so the tilting is less, resulting in sufficient stability to get the 1-ferrocyanophen with a heteroatom. And the reason behind is that it is the relatively large atomic radii of these heteroatoms which affords less tilting of the CP ring and thus gives greater stability in comparison to the carbon bridged ferrocyanophen. Now there has been synthesis of, like examples I am showing you, Sila 1-ferrocyanophen or Germa 1-ferrocyanophen, where the bridging atom is silicon or a germanium. There has been synthesis of tin as a heteroatom, Stana 1-ferrocyanophen or Phosphor 1-ferrocyanophen or sometimes sulfur or selenium bridged 1-ferrocyanophen. And these have been very recently done. You see, 2007, Ian Manners from UK has been engaged to establish the synthesis of these heteroatom incorporated 1-ferrocyanophen. Now, why he became so much interested about 1-ferrocene is the reason is that whenever a heteroatom is being incorporated within this ferrocyanide molecules with the bridge, like a bridging atom, then the CP ring gets tilted a little bit and it becomes strained. So the ring becomes strained, and because of the strainous ring, they are wonderful molecule for polymers, especially ring opening polymerization purpose. Like for example, you see the first 1-ferrocyanophen has been, which is the silicon bridged one, was first synthesized in 1975, but then people didn't know how these silicon 1-ferrocyanophen would be used, which was recently understood that these highly strained feature led to the ring opening polymerization, very easy ring opening polymerization reactions leading to organometallic polymers, especially ferrocene polymers. And these ferrocene polymers are very interesting that they have a very good solubility, and they can be at least, it is being tried to understand their degradability so that it can be used in today's undegradable polymer time. So the discovery in the early 1990s that strained ferrocyanophen undergo ring opening polymerization to high yield molecular weight polyferrocenes have provided additional motivation to the development of this exciting field. So this becomes a motivation to prepare different kinds of ferrocyanophens with different bridging atoms, with different number of bridging atoms, so that we can understand these molecules and get to know their polymerization prospects in latter years. So let me come to another strained organometallic rings. So the first strained metallocyanophen, basically the ferrocyanophen, was prepared was 2-ferrocyanophen. That means with 2 carbon bridging in 1960 by Reinhardt et al. Now he synthesized it very comfortably using a fulvalin and then condensing those fulvalin, and then later on using ferrous chloride to make 2-ferrocyanophen with a C2M4 bridge. Now very importantly, when that time the structural characterization was not done, so it was not understood that time, but later on when structural characterization was undertaken, then what people observed is that there is a ring tilt of around 23 degree, which is sufficiently, because usually if you see in case of ferrocene there is no tilt, so it is straight, right? Ferrocene is straight, but then in this 2-ferrocyanophen it has a ring tilt, and very interestingly, you see this is the ring tilt, and very interestingly the distance between the 2 CP are relatively shorter, which is 2.27 angstrom in this side and 3.32 angstrom in the greater side, more higher side. So there are 2 different height between the 2 CP ring, and this especially this ring tilt gave a strain to these type of ferrocyanophen and results in something like this ring opening polymerization, very easy ring opening polymerization. That means low temperature heating, you can get a polymerization like this. So understanding the ring strain, let me just clarify the ring strain a little bit. You see, this is for the simple ferrocene where you don't have any ring tilt. So delta is 180 degree and there is no ring tilt. So the alpha or the ring tilt is 0. Okay. But in this case, you see, the second one, there is a ring tilt and the delta is less than 180 degree, and the angle alpha, which is something like this from between the 2 CP. So this is the diagonal angle between the 2 CP alpha, and this angle is the beta. So if you can properly identify, this is the angle beta, and the angle within the heteroatom is theta. okay, within the bridge is theta. So the ring tilt measurement is being done with all these parameters. So alpha, beta, theta, and delta. And it has been understood that as the ring tilt increases, so you see, as we go from ferrocene to silaferrocene to phosphoferrocene to sulfaferrocene in this direction, what we get is the more towards right, the ring tilt is getting higher. So in silaferrocene it is lower, phosphide is slightly higher, and then in sulfur it is more higher. And you can see the alpha, the angle in this case, you see alpha, it is 0 in this case, ferrocene. For Sila it is 20.8, phosphor 26.7, and as we go to sulfur it is 31.1. And when the ring tilt increases, then what happens is that the HOMO-LUMO gap decreases, and that's why you see the UV visible spectroscopy shows an increase in the wavelength, and also the color intensity also increases. So this is how it happens. So as you go from 0 to 10 to 20 to 30 to 40, the alpha increases. That means the ring tilt increases, the energy of that particular ferrocenophane also increases in this direction. Now, as the energy increases, it becomes easier for a particular ferrocenophane to take part in ring opening polymerization. Okay, so as the strain increases, the ring opening polymerization becomes easy. Now these things have been going on for some time, for the last 5-6 years, and it has been observed some ring opening polymerization has been achieved with a heteroatom with one silaferrocenophane, which gives rise to polyferrocyenyl silanes, and there are also two ferrocenophane, which is also of some strain, which has also been achieved for ring opening polymerization, where you see there is this ferrocene in between, and there are different types of methods for ring opening polymerizations using radical mechanisms, using cationic mechanisms, or using anionic mechanism. So I am not talking in detail of that, but the main purpose of my understanding of this ring opening polymerization is that these ferrocenophane molecule are very significant for this purpose of ring opening polymerizations, with their strain, with the involvement of the strain due to the bridging atoms. Let me also go to some very common synthetic routes for these ferrocenophanes, and then we will come to our synthetic route. So here you see very easily synthesized dilithium ferrocene, and then it is being treated with main group halides. So any main group heteroatoms can be used. Liberation of lithium halides, and what we observed is heteroatom incorporated one ferrocenophane. The same synthetic route, another synthetic route can be from just the organic part, where you have the main group incorporated CP rings and can be reacted with ferrous halides to get the same one ferrocenophane. For two ferrocenophane, there are different types of organic methodologies. One of them is the McMurray coupling. In the McMurray coupling, you might have studied the McMurray coupling in organic synthesis, where dialdehyde has been used with TiCl3 and zinc copper catalyst in a reflux condition to get this unsaturated 2-ferrocenophane. Again, this unsaturated ferrocenophane are very well known for their ring opening polymerizations using just a heat, very low heat, or almost like 110 degrees centigrade, you can get the polyferrocene like this. Now, depending upon the R group of these polyferrocenes, the feature of this polymer varies. So you can also you can also tune the behavior or the properties of these polyferrocenes. However, not much work has been done. A lot of work are on the research table. So I may not be able to tell you the exact details of the polymers at this moment. There are the synthetic methodologies for 3-ferrocyanophen. You see, compared to 1-ferrocyanophen and 2-ferrocyanophen, 3-ferrocyanophens are rather have a less strain than the previous two. Okay, but this doesn't restrict them for polymerization. Of course, they can be used for ring opening polymerization. Here is a synthesis of 3-ferrocyanophen. It is being used with sodium Cp, and then it can be condensed with the bromo derivative, dibromo derivative, and then with sodium and ferrous chloride, the iron can be incorporated, and this forms a 3-ferrocyanophen derivative. There are other synthetic methods called heteroannular cyclization of ferrocyanide propionic acid using polyphosphoric acid as a dehydrating agent. So here you have a monofunctionalized acid, ferrocyanide acid, which can be used to condense between the two CP ring to form a CO, you see, ketone bridged ferrocyanophen. This is, of course, not a very good yield method. However, this is being used much earlier in 1957 to 60s, but these are reported from that time. However, from that time, this because of structural, not understanding fully the structural behavior, the ring opening polymerations was not understood that time also. There are other methods: reaction of 1-acetyl, 1-oxo phenyl propenyl ferrocene with potassium hydroxide. So it is just a acetyl group in one side, and you can have a propenyl group here in another side, and you can condense this with potassium hydroxide to give internal Michael addition product containing two functionality. You see, this is one functionality and this is another functionality. This is basically a 3-ferrocyanophen where there are 3 carbon as a bridging unit. There are different other methods. I am not talking about different other methods, but some internal Claisen condensation reaction also happens with a acetyl group in one side and a ester group at the other CP ring, resulting in coupling between the two to result dione type of ferrocyanophen. A base catalyzed heteroannular cyclization of bispulvalin. This is also very well known synthetic method with sodium amide and THF, which gives rise to a 2 functionalization. So 1, 2, and 3. There are 3 carbon in the bridging unit, but 1 and 3 are functionalized. The 2 is not functionalized. So this is a difunctionalized ferrocyanophen. Because you see, more you functionalize the ferrocyanophen, it becomes easier to use them for different applications. There are different types of ferrocyanophen with a ketone. So in this ketone, you see the carbon is sp2 hybridized. Similarly, there is unsaturated ferrocyanophen. So all these are well known and has been synthesized some time ago, and they have been right now used for polymerization purpose. Unsaturated, this is the unsaturated ferrocyanophen. This unsaturated ferrocyanophen can be obtained by just the reduction of these ketone moiety, and we get the unsaturated ferrocyanophen. Because unsaturated ferrocyanophen are more easier for ring opening polymerization, so that's why they are also very significant molecule. 4-ferrocyanophen, if you just going higher up the bridging unit, we can go from 4 to 5 to 6 and extra, whatever you need. So 4-ferrocyanophen can also be achieved by just linking these two silyl chain to form a unsaturated ferrocyanophen. This is the unsaturated 4-ferrocyanophen because there are 4 carbon atoms here. 4 carbon atom can be derivatized. So different derivation can be done. With lithium aluminum hydride, you can have 1 unsaturation. So depending upon what you need, the ferrocyanophen molecules can be achieved. So here also another examples where you have a diacetyl moiety. It can go to 4-ferrocyanophen with 1,2-dione, 1,4-dione ferrocyanophen, 4-ferrocyanophen. There are also a lot of ring closing metathesis reaction. For example, this is a diallyl ferrocyanophen, 2-allyl group at the 2-CP ring. It can be used for a ring closing metathesis using a Grubbs catalyst, ruthenium based metathesis catalyst, to close this ring to form a 4-ferrocyanophen. Recently, this type of ring closing metathesis has been used for preparing chiral ferrocyanophen. So here you see there are 2 ferrocyanophen which is achieved. So EZ isomers of ferrocyanophen. So this is where the double bond with the E configuration, and here you have a double bond with the Z configuration. Now the E configuration is actually optically active to give 2 enantiomers. So this is very recent work on reported in 2022, and it shows that these ferrocyanophen techniques, these synthetic techniques, can be used to make a chiral ferrocyanophanes. Now chiral molecules are very interesting because of their applications in asymmetric catalysis. Of course, these 4 ferrocyanophanes have less ring strain, but still they can be used for ring opening polymerations to get unsaturated and conjugated ferrocene polymers. So therefore, they are also of very interesting. Now, if you say different carbon bridged ferrocyanophen, so I will talk about carbon bridged ferrocyanophen now, and you can see here different examples of carbon bridged ferrocyanophen with different M. So here you have 1, 2, 3, 4, and 5. This is the 5 ferrocyanophanes. This is also 5 ferrocyanophen with different functionality. There are also different number of, you can vary the number of N depending upon the substrate you use, and we can prepare different types of ferrocyanophen with different number of carbon and different types of functionality. Why I am pointing out into this functionality, because you see, more the functional ferrocyanophen we prepare, we can easily able to tune the properties of the ferrocenes so that to use it for different applications. So basically, different types of functionality has different behaviors, and we can use it for different applications. And of course, there are large variety of ferrocyanophen prepared with different types of conjugated behaviors. So these are conjugated ferrocyanophen. You see that ring are bridged within themselves, where the pi electrons can be easily travel from one side to the other side. And please understand that when these ferrocyanophens will be polymerized using a ring opening polymerization method, then this will give rise to a conjugated organometallic polyferrocenes, which are very interesting for for conjugated polymers. Okay. There are different other applications of these ferrocyanophanes. For example, one of them has been used as a cytotoxic agent very recently, and these are in the phase trial. There are ferrocyanophanes where asymmetric type of the chiral ferrocyanophen. You see, this is a chiral ferrocyanophen where this is the chirality is at the 1 position, and also the chirality as the 2 position, giving rise to a chiral ferrocyanophanes. Now these chiral ferrocyanophanes are very good catalysis. They have showed that these can be used in asymmetric catalysis. So basically what I mean to say is that when we have different types of functionality, we can actually play around with these ferrocyanophanes to get more vast type of ferrocyanophanes which are of different applications. So with that in our understanding, we try to understand the ferrocyanophanes, and what we try to look into is that what happens if we have functionality on a 3 ferrocyanophen. 3 ferrocyanophen means there are 3 carbon bridged ferrocyanophanes, And if we can functionalize all the carbon with different types of groups, so can we achieve that? Because this type of ferrocyanophen is not there in the literature, and it has never been prepared. So di-functionalization is prepared, monofunctionalization is prepared, but tri-functionalization, because that means all of the carbon in this 3-ferrocyanophen is being functionalized with some functionality, not prepared till date. So we thought to use our own synthetic methods to prepare some of these functionalized ferrocyanophanes and understand their behavior. So another very important thing is that what we also thought at that time is that if we get all the 3 carbon atom functionalized, what we get is chiral ferrocyanophen, different number of chiral ferrocyanophen. For example, if we can achieve 3 functionalization, so that means all the 3 carbon atom can be functionalized with different functionality, then actually what we would have got is that there could be enantiomers, that means 3 stereogenic centers, and if there are 3 stereogenic centers, then we would end up in 2 to the power 3 isomers. So that means 8 isomers are possible. So 8 isomers can be used to understand their properties and then understand their applicability. However, these are all not known in the literatures, because tri-functionalization is not synthesized till date for this 3-ferrocyanophen. Now our initial study shows, so let me come to our study now, and we will show you that how we have been able to get such a very difficult ferrocyanophen. So this is the initial study where we started. We took dialdehyde ferrocyanophen, where the cypirine has been functionalized with a aldehyde group, both the cypirine in an aldehyde group, and we took acetyl pyridine, and we reacted this in a red mud supported reaction. Again, I have told you that we initiated this solid support synthesis because of some reason, because we were not getting enough yield and selective products with solution chemistry. So we tried this solid supported reactions, and we have been able to do solid supported reaction till date. So red mud supported reactions are very interesting because red mud contains alumina and it is alkaline. So we thought to use this alkalinity and also alumina containing alkalinity for preparing some of the very interesting compounds I will let you know. So what we get is a monofunctionalized product. So one of the aldehyde is being functionalized with the enone, whereas the other aldehyde remains pendant. So that is the selective nature of functionalization I am talking about, which we obtained with the red mud support. Now this is a very initial study. Later on, what we saw that this selective functionalized ferrocene, when reacted further with acetyl pyridine in a solid support condition, in a heating condition rather, what we get is either a symmetrical difunctionalization or a unsymmetrical difunctionalization, which is very unique. Unique in the sense that if you see this part, this is actually a 1,4-Michael addition product. So we'll give you a little understanding of this 1,4-Michael addition product, how we obtain. So the mechanistically, if we see a little bit on the mechanism, then it is like the nucleophile can attack either the aldehyde here. So this is the blue one. So this is the aldehyde attack, which forms the product which is symmetrically functionalized, this one. And if the nucleophile attacks from the top position of this olefin, so this is the 1,4-Michael addition I am talking about. So this is the 1,4-Michael attack from the top position of this olefin. What we get is this one, which actually gives rise to the product which I am talking about, the 1,4-Michael addition product. This is the unsymmetrical 1,4-Michael addition product. There is another way of attack by this nucleophile is by the down method. You see, this is the pink uh, color attack, which is the one for attack from the down. Now, if this nucleophile attacks from the down, it will lead to another isomers, which of course we didn't observe. So that means the Redmond supported reaction actually selectively gives rise to the top attack, the top 1,4 attack, and leading to this particular compound 3. Okay, now what is the big thing of this compound 3 is that okay, so what is the big thing of this compound is that, so these were already properly characterized with structural analysis, and it shows, so this particular is the 1,4 Michael addition attack. I will just concentrate on this part, is that they perform, so the nucleophile attacks the olefin rather than the aldehyde. Okay, and we got a 1,4 Michael addition product. Now, when we got this particular result, we extended our thinking to some proposed scheme, because if a 1,4 Michael addition occurs with this type of solid supported condition, then it can also happen that this nucleophile can attack both the olefin in a 1,4 Michael addition type, so blue type and the red type, simultaneously. And when it is done, if it is simultaneous, it can simultaneously attack the two olefin, then it will lead to a double Michael attack, and of course lead to a 3-ferrocyanophen with triply functionalized carbon bridge. So that will serve our goal. Another proposition, what we try to understand is that the compound what we got is the 1,4 Michael addition initially, where one of the aldehyde is still remaining pendant. So that can be used by the nucleophile for an attack at the aldehyde to get something like this, and then again another Michael attack from one of the nucleophile can give rise to a ferrocyanophen, which will give rise to ferrocyanophen with trifunctionalization. Okay, so this is called a stepwise Michael addition. So first Michael addition happened to form the 1,4 Michael addition product, and the second Michael addition is this one, which will lead to the ferrocyanophen. So this is our thinking that time. We didn't have any idea whether we will succeed or not, but by the God's grace, this solid state synthetic approach, supported approach, gave us that compound where we have achieved the formation of 3-ferrocyanophen. You see, there are 3 carbon bridging, 1, 2, and 3, and all the 3 carbons are functionalized with a acetyl pyridine here, with a CH2CO pyridine here, and with a CH2CO pyridine at carbon 3. And this is being achieved when we use the symmetrical dipyridine function ferrocene with acetyl pyridine in a red mud condition and at 70 degrees centigrade for 12 hours reactions. So this gives rise to this particular ferrocyanophen. You know, unexpectedly, another very important compound also obtained. So this was structurally characterized. We got the structural characterization very easily because these were very polar compound, and we got this. You see, these are the carbon atom, bridged carbon atom, and these bridged carbon atoms are functionalized. Another very unexpected thing happened is that when we use the solid supported approach with another of our 1,4 Michael addition product where the aldehyde is pendant, to use them in red mud condition, and what we get is this one where the aldehyde part is being functionalized, and then what happened is that we extended our reactions to almost like 24 hours, when what we observe is that the nucleophilic attack happens, which is again a 1,4 Michael addition, similar to what we have thought of. So when this type of attack happens, we get similar ferrocinophane. We first thought that the ferrocinophane what we obtain here is the same as the previous one, but actually it is different because they have a different orientation of these moieties across the bridge. So therefore, when we compare these two, so we structurally characterize this one also, and if you see the structural characterization, so this is the solid state 1-port synthesis we got. So we also tried this to prepare these two isomers in a 1-port conditions, and we achieved that 1-port condition. Okay, sorry. And what we understand is that these two ferrocinophane are diastomeric in nature. That means that the chiral center here within this carbon, within this bridging carbon, is actually have a different orientation within these two molecules. And when we try to understand in a chiral manner with Fischer type of orientations, what we observe is that this is a meso compound. So the way we understand a meso, where there is a plane of symmetry, you see there is a plane of symmetry here, and because of this plane of symmetry, this is a meso compound. But the other one didn't have a plane of symmetry, and we thought that this must be an enantiomer. This must be a racemate of two enantiomers. So we tried our best to understand it properly. We tried to understand the mechanism, how it actually obtained. So mechanistically, just if I take 1 minute to make you understand the mechanism, you see what we observed is that what we obtained. So we went back and tried to understand the initial story. So here is we have a dialdehyde. There is a nucleophilic attack at the aldehyde in presence of red mud support, and when we get the dialdehyde, so this is the dialdehyde, this is the monoaldehyde one, this is the product what we obtained here, compound 1, and then there is further nucleophilic attack by the nucleophile, and of course there are two types of attack. One attack goes to the aldehyde, which gives rise to the so one attack gives rise to compound 3. The attack is at aldehyde, and later on more of such nucleophile attacks the olefinic carbon, leading to a double Michael addition. So this is the double Michael addition I am talking about, and this double Michael addition gives rise to compound 6, which is the chiral one. Whereas the other type of attack, if you go to this pink attack, pink arrow, what we got is the first 1,4 Michael addition attack, and then another nucleophile gives rise to the second 1,4 Michael addition attack, where this second 1,4 Michael addition results in a ring closing approach, resulting in the meso compound, because the direction of attack is always different in these two compounds. So therefore we got two different isomers. Now we try to analyze further. What we achieved is that although we have functionalized all the 3 carbon atoms, bridged carbon atoms, but the functionalization was something like this, that the 2 of the functionality is the same. So one of the functionality is different. So when such situation comes, it should be that there should be 2 to the power 2 isomers. That means if we try to understand in an organic manner, so if you have chiral behavior where you have both the R group same and they have a different functionality here, then we must get there are 3 chiral centers, but then the 2 isomers would be same. So in that case, there would be 2 to the power 2 isomers, that is 4 isomers we will get. So similarly, from our approach also, what we understand is that we got 2 to the power 2 isomers, that is 4 isomers, and among the 4 isomers, we have got a racemate of this 6, so 6 and 6 dash, and the meso for this one. We didn't get the fourth one, and we tried a lot, but we didn't get the fourth one. So we end up in saying that probably the attack which gives rise to the fourth one is not feasible. We have also done the we have also done the chiral HPLC. The chiral HPLC shows that there are 2 peaks. That means the chiral HPLC of the 6, the racemate. That means they have 2 enantiomers, 6 and 6 dash. The enantiomers I have drawn here. You see, this is one enantiomer, and the other one is this one. So we have done cyclic voltammetry to understand the electroactiveness of these ferrosinophanes, and we have seen that very pretty reversible character of this ferrocinophane. We have also tried to understand if we use different functionality. For example, in the earlier case, we were using pyridine as a heterocyclic ring. In this case, we used thiophene, and in thiophene case also we got the similar type of isomers. So this is the thiophene incorporated 3-ferrocinophane, and of course I have already told you that these are not known in the literature. And the not known in the literature is the fact that not all carbon of 3-ferrocinophane is functionalized. So this is the first time I am showing you these type of examples, and we have communicated this to journals recently in the revision stage, and we have got the crystal structure of this thiophene ferrocinophane as well. So we wanted to try this to get some applications out of it. So let us see. You see, very initially we did it. Now because we have functionalization where we have a basic pyridine unit, so 3 basic pyridine unit we could able to link to these carbon chains. So what we try to understand is that why not to use them for sensing of picric acid. You see, picric acid is a toxic compound, and it is being used to prepare bombs. Okay, so therefore, if you can use this ferrocinophane for the sensing of picric acid, that probably will give lot of proper applications in defense sector. So therefore, we tried to sense this picric acid, and we thought that because this ferrocinophane contains 3 pyridine unit, so 3 picric acids at a time can be sensed by this ferrocinophane, leading to low level of picric acid detection. We continued our study, and we did our experiment, titration experiment, electrochemical sensing of picric acid, and what we observed is that yes, it deviates the potential of ferrocin, the oxidative potential of ferrocin, as soon as the picric acid is being interacted with the pyridine unit. Because what happens is that because of its high acidity, the picric acid actually interacts with this basic pyridine N, leading to some type of interactions with its OHN type of interactions. So similarly, OHN type of interaction. But what we didn't observe is that, so we only observed 2 of the picric acid to be interacted with the 2 of the pyridine unit. Rather, 1 of the pyridine unit remains vacant because of steric factor, because of approach factor, because 3 picric acids could not able to approach the 3 pyridine rings. So therefore, it's a 2:1 type of interactions what we achieved, and we also saw a color change. And when we tried with other similar type of compounds, like for example dinitrotoluene DNP, or nitrotoluenes, or different types of nitrotoluenes we tried, nitrophenols even, what we got is the selective nature of interactions with the ferrosinophanes I have talked about, and we got 1:2 interactions, and the limit of detection is very low, is almost like 9.6 nanogram per mole per ml, which is almost very interesting because this type of picric acid detection is commonly not in the literature. So we did some computational study to understand the picric acid interactions. So here we show the interaction of two picric acid. You see the yellow part where there is a hydrogen bond between the N and the H of the picric acid, of the OH of the picric acid. We also did, we tried to understand it in a, by using NMR, titrations inside the NMR tube. And what we observed is that there is a shift in the picric acid peak as well as in some other peaks when we are trying to interact the ferrocyanophen with picric acid in either 1:1 manner or 1:2 manner. Till 1:2 there is a shift, but with 1:3 the shift is not large. So therefore we came to a conclusion that two of the picric acids, so two equivalents of picric acids interacts with the ferrocyanophen, giving rise to at most 1:2 interaction. We also tried to understand the picric acid sensing in vapor phase because it has been seen that there are a lot of terrorist activity where terrorists used to carry picric acid in metal boxes, and it is very difficult to understand whether it is a picric acid or different kinds of powder in it, and they put those in different carriers. And there has been some cases where blast has took place using a Tiffin carrier. Okay, so therefore we try to understand whether this picric acid can be sensed in form of a vapor, because Tiffin carrier, although it is blocked some way, but the vapors definitely comes out. So sometimes vapor phase interactions is very important, sensing of vapors, picric acid vapors. So when we tried that, we also saw that there is a slight deflection of around 40 millivolt when a picric acid vapor was interacted with the ferrocyanophen. Another very important thing what we try to understand is that we try to fabricate this in a device, to make a device, and however this is very initial stage, and we fabricated a device and we tried to get the current voltage curve. What we observed is that as we are adding picric acid, we are getting increase in the current part, and this current part has been used to understand to get this device fabricated. Okay, so this is what I wanted to deliver. Concluding session summary: we have been able to prepare a diastomatic 3 ferrocyanophenes with 3 different functionality at the 3 ferrocyanophen moiety, using a double Michael addition approach, and of course using a green synthetic methods, using a solid state synthetic methods, using red mud as a synthetic is a solid support. We have also tried to understand whether this particular ferrocyanophen can be interacted with picric acid. Again, if we can able to sense picric acid, of course this will be a major challenge, but then if you can do it, it will be a nice applications towards the defense area. With this, I acknowledge my students. I of course acknowledge your professor, Dr. Abhishek Ghosh, and in this picture also you will find him standing straight, and I am very much thankful that he has been one of my students some time back, and he has initiated a lot of studies which still we are going on. And also I want to acknowledge Viplav Haldar, who is being mainly associated with the work of ferrocyanophen, and recently Madhusri Jana, and of course Madhusri Jana is also a student of Medinipur City College, who is also doing her 1 year coursework, and after this coursework she will be starting her, although she has already started her work. And I am very thankful to Medinipur City College that you are creating so much of effort to give very good students to us, so that we can use this opportunity, use your good students' brain for making such a interesting chemistry out of it. I also thank different agencies like DST Feast, CSIR for giving me money for the project I am working on. I also thankful to some of our collaborators from Japan, Sasamuri and Professor Sasamuri and Dr. Wolpert from University of Education, and also we have been indebted to Professor Madhurima Jana, who has been working with us for some theoretical chemistry, for some simulation studies at NIT Rourkela. And of course, thank you all uh, for your listening and wonderful audience uh, at at the online stage. Thank you very much.
Thank you, sir.
So if you have any questions, I would
Thank you.
love to
Thank you, sir,
interact
for
with.
giving your precious time for to us. And student, you have any question? Student, কারোর কোনো question আছে? Sir, I have one question.
Yes, please.
Pyridine, trinitrotoluene, sir. Pyridine moiety is sensing that trinitrotoluene.
Yes.
Sir,
So can you repeat? Can you repeat?
sir, you have shown a compound that is trinitrotoluene,
Yes.
pyridine-based compound, ferrocin linked with pyridine.
Yeah, no, that is actually we are trying to sense trinitrophenol.
Sorry, trinitrophenol, sorry.
Okay, trinitrophenol. Now, when we try to sense the trinitrophenol, the trinitrophenol actually linked with the pyridine unit in form of either hydrogen bond or some type of interactions. We have not been able to understand that yet, but it forms interactions, very genuine interactions. It happens, but other trinitro derivatives doesn't form such interactions. So that's why we have been using that for sensing purpose, because you see there are 3 pyridine units oriented at different directions. Okay, so it can grab the trinitrophenol in form of vapors or in form of liquids and interact with them and to give the electrochemical sensing at the ferrocin unit.
Hello, Saurabh. Wonderful talk.
Yes.
I'm C.R. Sinha.
Oh, so sir, just before you start, let me also put it like this: that I am really grateful that I am giving a talk to an audience, where in the audience I have my student as well as my teacher.
Thank
So
you.
thank you very much.
I-
Please go ahead, sir.
I have one query.
So that's a
Here is
wonderful
also
to
one-
me.
one-
I'm really astonished
you know,
to
one
make a
audience
presentation
is
like this.
Professor Bosak, Amit Bosak also. He is also in audience.
Yes.
Okay, one query. In your picric acid, you have shown the LOD around 10 to the power minus 5 molar, or like that.
Sir, yes, you want to know that picric acid, how it is different, or
No. My query is there are many other sensing technologies now available, but
yes. There are
what's the
picric acid can
advantage of
sense
your
between-
since your material that is a sensor that is too costly, and its preparation is also too tough, characterization also tough. So what's the advantage of your sensor, since there are low cost, cheap, and easily available, affordable chemicals are available? Then what's the advantage of your sensor?
Yes, sir, you are right. So there are material available. There are even sensor available, but those sensors are actually fluorescent sensing. So either fluorescent sensing or color change. So they give rise to a color change. But the problem happens when there is a picric acid. If you have seen the picric acid, these are very dark yellow in nature. And when those picric acid interact with the material, although it gives rise to a color, but the level of picric acid which gives rise to a color sometimes differs. But the electrochemical sensing actually gives rise to a very low level of sensing ability, rather than fluorescence and other spectroscopic levels. So they mostly sense in a micro level. But when we use in an electrochemical manner, then in the electrochemical sensing method, the picric acid can be sensed in a very low level, so especially in a nanomolar level. So that is what why the electrochemical sensing sometimes gives rise to a better result than fluorescence type of sensing or color differentiating sensing.
Is there any fluctuality in your ferrocenyl compounds? Fluctuality. Will they have some effect on the sensing process, or there is no such impact?
We have to check actually, because we have been able to get this ferrocyanophen in a very recently, and probably we can use different functionality. For example, the last one we got is a thiophene functionalized ferrocyanophen, and thiophene, you see, when it is a sulfur, it can sense heavy metals. So that also we are trying to do. Although we have did some sensing for unsymmetrical ferrocyanide compounds, which I have not talked here. I have only talked here the ferrocyanophen part, where there is a bridging between the two CPD.
Okay, okay. Thank you.
স্যার থ্যাংক ইউ। ফাইনালি আমি একটা কথা স্যার বলতে চাই যে আমি খুবই সামান্য কিছু কাজ করেছি, কিন্তু যেটাই করছি সেটা আমার কিছুই নয়, যেটা স্যার শিখিয়েছেন ওই স্যারের প্রফেসর সৌরভ চ্যাটার্জি স্যারের যে শিক্ষা সেটাই হচ্ছে। আমি জাস্ট এখানে দাঁড়িয়ে আছি মাত্র। ওনার কাছে যদি আমি না পিএইচডি করতে যেতাম, আমার পক্ষে কোনো কিছুই করা সম্ভব হতো না। বা আমি এখনও যেটা করি আমি সেটা মনে করি না কি আমি নিজের যোগ্যতায় করছি, উনি যেটা শিখিয়েছেন সেই শিক্ষাটাই আমি জাস্ট অ্যাপ্লাই করছি মাত্র। থ্যাংক ইউ স্যার।
Thank you very much, Abhishek. But I also like to tell you that whatever I am, I have tried my level best to make you learn. I have also learned from my teacher who is sitting beside you, Professor Sinha, Professor Chittaranjan Sinha sir. Thank you very much for such learning, so that I have been able to, give it to my students, and then probably my student will also give it to the other students to make it work. Thank you very much.
থ্যাংক ইউ স্যার। থ্যাংক ইউ। থ্যাংক ইউ ভেরি মাচ স্যার।
Thank you.
Many thanks to our distinguished speaker for this session. Now we are heading towards the next step of our program.
We are fortunate enough that Professor C.R. Sinha and Professor Bashak are now here with us. We would like to felicitate them with our students.
Now we would like to request Professor Moidul Hossain to kindly chair this session.
Hello.
It's our privilege to welcome Professor Amit Basak for this lecture. He is a prominent researcher. He done his PhD degree in Calcutta University under the supervision of Professor S.K. Talapatra. He is the postdoctoral fellow of Johns Hopkins University, USA. His specialization on the field of DNA interacting agents, asymmetric synthesis and enzymology, diradical chemistry, capture chemistry, etc. He has a vast teaching experience and he get many prestigious awards like J.C. Bose National Fellow, Fellow of Indian Academy of Science, Fellow of Indian National Science, Fellow of National Academy of Science, Fellow of West Bengal Academy of Science and Technology, Fellow of Royal Society of Chemistry. So, I welcome Professor Amit Basak to deliver his lecture. Thank you, sir.
এটা পকেটে আচ্ছা এই পকেটে দ্বারা মোবাইল দিয়ে পকেটে নেই পকেটে মোবাইলটা রয়েছে এক সেকেন্ড এটা এখানে হ্যাঁ এটা তো সেই দাঁড়া এটা হচ্ছে এটা লেজার এটা হচ্ছে নেক্সট ঠিক আছে হ্যালো am I audible to everyone at the back? Am I audible? You can come forward. I think, why are you sitting at the back? Come forward because I want to show you something also. There are so many empty seats. All seats are equal. Treat them as equal. Okay, so what is the duration of this talk? Stipulated duration? 30 to 40 minutes. Okay. So let me start by giving a thank you note to Dr. Hussain for introducing me to the audience. And still, I think they can come forward. There are so many chairs. Why you are sitting at the back? Maybe I will come here. If they don't want to come, I will go straight away up to them. come to the front because I want to show you. You cannot see, you will not be able to see what I want to show you today. Ajay. Yes, this is actually a lecture which will actually aimed for the students. For the students or teachers, those who are in the teaching profession, you can excuse me for giving this talk. When Abhishek called me, I said I have nothing to show you in green chemistry, but I can give some very fundamental, I can deliberate on some fundamental concepts in organic chemistry. He said, whatever you say, sir, you go ahead and talk. So with that aim, I came here today from Calcutta, all the way from Calcutta, and I know that because the topic I will be presenting needs very, it's a conceptual thing. So my presence is required. Otherwise, I could have given it online, but I thought that online will not be sufficient to express the feeling that I want to give to you. Okay. Now you see the, first of all, I can show you there are two institutes side by side. This is IIT Kharagpur. Maybe you have visited already. It is so close from here. And this is what is IISER Kolkata. Why two institutes? Because I was there at IIT Kharagpur for 30 years. And then after retirement, I went to, and I have been now associated with IISER Kolkata. So these two institutes, especially IIT Kharagpur, because my whole life is basically developed there, that whatever science I did, okay, little science, not much. And IISER is basically what you call Vidhashram, means where you spend your last days, last years of your life, okay. But it's always good to be associated with an educational institute throughout, so long as your health permits. Also, there is one duty I should do. I thank Midnapur City College for inviting me. The principal is here, and Abhishek is always there. And also I see earlier research scholars, now your faculty member, they are also here. So it's very good to see that this college is flourishing so well. I came here about 5 years back, if I remember correctly. And then now, as I was entering, I saw a lot of activities. That's very good. Okay, now let us go to the topic. It's a topic on chirality. And I say that a topic of endless curiosity also. Now chirality, actually what happens, many things we actually have taken for granted. Like we never realize that how chemistry has dominated our life. Right from the morning when you brush your teeth, you start putting the paste and brush it, okay? The material that is, the material which the brush is made of, or the paste, whatever you are using, all are formed from very basic chemicals. So chemistry, you start the day with chemistry. You also end the day with chemistry. Especially people like us, we took a sleeping tablet or a hypertensive, anti-hypertensive tablet, and that is our end of the day. Similarly, chirality also, we don't realize that how it is dominated in our life. I'll give you a small example. When I was at Presidency College, when I was a student of Presidency College, so I used to take a bus from our, from where we are staying. That was a little bit far off from College Street. Now the bus, you know, that Calcutta buses, especially those days, were so crowded, it was very difficult to get inside, okay? That is number one. Number two is also, sometimes you have to get inside the bus while the bus is also running, while the bus has started. Okay. So I was there waiting for the bus, and also the frequency of bus was very few. So if you miss the bus, you are going to miss the class also, the first class, which was usually, the lecture was given by a famous physical chemist, Professor Mihir Chaudhary, who is no more today, but he always starts the day with the physical chemistry class. So you will miss the class. So what happens, the bus came, okay, usually at say 9 o'clock, and it, before I get in, it started running, it has started. And I took the handle with my left hand. And then I actually fell from the bus. Had I took the bus with the right hand, I would have got inside the bus. Okay. That day, I realized the importance of chirality. Because the bus was moving, and you take the left hand, and left hand allow you to move on this side. On this side means out of the bus. So I fell from the bus. Fortunately, I was safe because the bus behind, there was a bus behind, but that actually took a turn. So I was safe. So that is one chirality, example of chirality. Okay. Sometimes in a hurry, if you try to put the wrong shoe in the wrong foot, you also realize the pain that it gives. So that is the example of chirality. Like in cricket, we have a cricket bat. Now the question is, we see so many right-handed batsmen, left-handed batsmen. And they play equally well almost. Why? Because the cricket bat does not have a chirality. Cricket bat does not have a chirality. So it doesn't matter whether you are left-handed or right-handed. But a glove, if you want to put a glove in your hand, that has a chirality. You cannot put the right-handed gloves onto the left hand, or vice versa. Okay. So what I basically say that chirality is omnipresent in our life. We take, suppose in the morning people are prescribing some drugs, we are suffering from some disease, say we take a penicillin drug. We don't realize that penicillin is chiral molecule. And the moment you destroy or change the chirality in penicillin, it no longer acts as an antibiotic. Okay. But these are, as I say, these are taken for granted. We take so many anti-malarial compounds, anti-diabetic compounds, anti-hypertensive compounds, then so many drugs, our mood, anti-depression compounds. Mostly they are chiral molecules. And as I said, moment you change the chirality, chiral center, as you know, because you are all students of chemistry, I believe all are chemistry, and they are coming from this college as well as nearby colleges. Okay, so that is very good. The chiral center, if you change, it loses the activity. Okay. Now, where from all these chiral molecules come? There are many ways, but the best way is to get it from nature. I think that is the only connection I have with green chemistry, because these drugs or the material that we have, which are useful, if they come from nature, you will see they usually have chiral centers built in it. They are usually chiral. And the chirality is of one type. You know, chirality actually are two types. One is left-handed chirality, another is right-handed chirality. These are. But nature makes only one type of chiral molecule. And they are active only in that form. If you take the other chiral form, that does not work. That does not work, but that may have other activities. Okay. So that is, as I said, chirality is omnipresent, but it's always a growing subject. Unfortunately, these days we don't stress on the very basic fundamental concepts of chirality. We give so many examples of asymmetric synthesis, but we don't really go to the genesis that um, in that depth to explain the chirality. Okay, let's see what is in store. As I said, these are, I think, you all know, because these have been taught to you, that what property makes a molecule chiral. What property makes a molecule chiral. Achha, remember that we actually we are living in a three-dimensional world. Okay, and the molecule that we call chiral are actually if you had a four-dimensional world, then that chirality will be lost. Okay, means fortunately we are not living in a four-dimensional world. We are living in a three-dimensional world. So the molecules that we call chiral are chiral in three dimensions. Okay, they are not chiral in two dimension. They will not be chiral in fourth dimension world. Okay. Okay, so that means there is some relation between chirality and dimension. Now this aspect also we don't realize, we don't tell to the students. Okay, like there are, you know that chirality historically, when Pasteur, you know Pasteur actually first isolated the chiral tartaric acid and then also lactic acid. And Van 't Hoff and Lovell, they explain the genesis of chirality by saying that there must be a carbon in the molecule which will have four different substituents, and that carbon will be called an asymmetric center or a chiral center. And also Van 't Hoff and Lovell, without doing any experiment, they propose that the carbon is tetrahedral, because carbon cannot be planar. If it is a planar, square planar geometry, then chirality will never happen, because it becomes a two-dimensional molecule at that time. As I said, that as these molecules, we don't realize that these molecules are chiral only in three dimensions. So from that concept, Van 't Hoff and Lovell, without any extracrystallographic studies, hybridization was not there at that time. BS-EPR theory was not there. But they predicted that carbon is tetrahedral. And because it is tetrahedral, when you have four different substituents, that gives chirality to the molecule. Okay? Now, this type of carbon, when present in a molecule and makes the molecule chiral, is called central chirality. Central chirality. This is the historical origin. So people thought that molecules are only chiral when there is a carbon or when there is a chiral center present in the molecule. Okay. Now things started changing later on. Later on what happened? People found that even such centers are present in a molecule, those chiral centers, but the molecule may not be chiral. Like meso compound. Actually in the previous lecture we have heard that there was the meso compound, tri-substituted ferrocene, so the meso variety. So even if there are chiral centers present, the molecule may not be chiral. Okay? So the scientist, what is the example? The example is mesotartaric. That was the first example. Okay? And then science progressed more, and they found that molecules where there is no such carbon present, no chiral center as such present in the molecule, but the molecule may be chiral. What is the example? Examples are chiral allenes, chiral biphenyls, which are actually orthogonal to each other, and but there is no chiral center. Okay. So when teaching chirality, we also tend to make a mistake by saying to the students from the very beginning that chirality is due to the presence of an asymmetric center or a chiral center, nowadays called a stereogenic center, because that goes into the mind of the student and gets into the brain. So they cannot really, later on the teacher must be saying that, oh no, the first day I said this, but there are molecules without any chiral center, they may be chiral. Okay? So that creates confusion. So always we should say that historically it was the first discovered that the presence of chiral center is necessary. But then science changed, and people started looking at the molecule as a whole. And they started to find what is the requirement for chirality. And they basically found out certain elements of chirality. One element of chirality is the existence of chiral center, and that is what is called central chirality. Okay. What are the other forms of chirality? I just said chiral allenes or chiral biphenyls. They have axial chirality because they have a chiral axis. What is the chiral axis? A line where two sets of ligands or substituents are present which are orthogonal to each other, and they are such that they destroy all symmetry, presence of the symmetry elements, not the simple axis of symmetry. All improper elements of symmetry are absent. Okay. After axial chirality, people developed another or found out another element of chirality, that is called planar chirality. Okay, now that's okay. That is called planar chirality, which is a little bit difficult to introduce to the students. The definition that is given in all the books, like Eliel's book, or Professor Noshipuri's book, or Professor Tolapatro, whichever standard textbook you take, they say that there is an element of chirality which is called planar chirality, and planar chiral molecules contain a chiral plane. What is the chiral plane? Very difficult to describe because a plane cannot be chiral, because a plane always has a plane of symmetry, which is the plane of the molecule. Okay. So always, as teachers, when I was introducing this planar chirality, it was quite difficult, quite tough to introduce the subject. Anyway, I will come back to that. So planar chirality is another element of chirality, and there was a fourth element of chirality that is called helical chirality. So broadly speaking, there are four types of chirality: central chirality, axial chirality, planar chirality, and helical chirality. Okay. Today I will be talking actually basically first planar chirality, that how to introduce planar chirality to the students. Okay. Okay. Oh, before that, I was just giving some examples. Why should we study chirality? Because chiral, I said, we have taken for granted that we live in a chiral world. But what are the applications of chiral molecules? One is various natural products as drugs. They have different chiral centers, as you see here. This is minus morphine. Minus is just their optical rotation. So that is minus morphine. You know, that's a painkiller, one of the best painkiller natural product. This is minus quinine, which is the anti-malarial compound. And look at the molecules of life. Our life is composed of nucleic acids, proteins, carbohydrates, lipids, whatever you say, amino acids, all are chiral molecules. So without chirality, we will not be living today. And the origin of life is directly connected to the origin of chirality, which is still a burning question, that from where chirality has originated. Okay. Many of the drugs, actually I found that about 70% of all the drugs that are in the market are chiral molecules. Okay. Now when you get a molecule from natural source, it automatically gives you one chiral form. But when you make a molecule, a drug, in the laboratory, what happens? You get both plus and minus. You get both the dextro or the levo. Or other words, you get both the right-handed or the left-handed molecule. So basically you get a racemic mixture. Okay. In the earlier days, like 1960s, the drugs which are synthetically made, okay, were all racemic mixtures, because that is easy to make. And you know, from racemic mixture you can separate the two molecules by a process called resolution, but that will add burden to the economy. The industrialists or the pharmaceutical companies don't want to spend money on that. And at that time, it was not also very clear that which molecule, the plus or the minus, dextro or the liver, which is active and which is inactive. That is also not clear unless you separate them and study them separately. So at those days, 1960, the synthetic drugs, remember, I am not talking about natural ones, synthetic drugs were sold as racemic mixture. So one sort of such drug was thalidomide. Structure shown here, very simple molecule, containing only one stereogenic center or one chiral center here, okay? And it was sold as a racemic mixture and given to pregnant women, okay, waiting to give birth to the baby. What happened? And why the drug was used? Because it gives, it's a sedative, it gives a sedation effect, and the pregnant lady felt much better taking the drug. But what happened? That the babies born from those mothers who were taking this compound, thalidomide, the babies born were found to be, they are defective. This is called birth defects, are having birth defects. Like I just give you one picture. The hands, you see the hands have not grown. Sometimes fingers will not be there. Sometimes the fingers will be all tied up. Sometimes you will not have ears. So they are all having birth defects. So then people started looking at it. What happened? Why this thalidomide, what is causing this birth defect? They found that the main cause of this is thalidomide, because it is only the babies born from mothers who were taking thalidomide, not from mothers who were not taking thalidomide. So thalidomide is the culprit. Now, okay, that is the culprit, but the problem is why thalidomide is behaving in such fashion. Okay, so they found that because it is given in racemic mixture, one of the compound, which is the R-thalidomide, you know the RS nomenclature system, right? The R-thalidomide is giving the sedation effect, which is actually called eutomar. Eutomar is actually, we have many nomenclature, isomers. Similarly, in biology, in a racemic mixture, the one which is having the desired effect is called eutomar, and the other molecule is called distomer, which does not have the effect. So this is a distomer. This is not giving any sedation effect. That is okay, but if contrarily, what happened? It is the molecule which is giving, which is the cause of the birth defect in the baby. So had the mothers been given only the R-thalidomide, it would have been okay, because it has the sedation effect and no birth defect activities. It is the other molecule, that is the other counterpart, that is given, that has given the genesis of the birth defect. So after that, the whole world became very conscious about the chirality of the drugs. So today, if you want to make a drug, and if it is a racemic mixture, you have to separate it, or you do it in an asymmetric way, and show the activity of both the compounds. And then if the FDA, you know, the Food and Drug Administration, which is very strong in United States. So if United States finally accept the activity of the two drugs, then only you can sell the drugs in the market as a racemic form. If you show that, okay, the other isomer is not it does not have any effect. So that you can use in the market. Like, we don't realize, we take levocetirizine. How many of you have heard of levocetirizine? Cetirizine, have you taken? Students, you don't take, no? You are not suffering from allergic reactions. This is very common anti-allergic drugs. Okay? Cetirizine. Earlier it was given as a racemic mixture, plus minus mixture. Now you have levocetirizine. Now you have S-omeprazole, which is antacid behavior. Now you have L-dopa, that is used for Parkinson's disease. So only one chiral form is given. Okay. So today that is the mandate. that you have to separate and use the drug in the chiral form. Now you can argue that if the other form does not have any effect, you can use it in the racemic form. Yes, in the market, cetirizine, racemic is also available, and levocetirizine is also available. Which will be more costly? Obviously levocetirizine, not the plus minus mixture. The problem with the cetirizine or any anti-allergic drug is that it reduces the allergic reaction, no doubt, but it also induces sleepiness in the person taking that drug. Okay, and they found that levocetirizine, that means the minus form of cetirizine, does not affect the central nervous system, which is causing the drowsiness. Okay, and if you take cetirizine, and if you want a good sleep, take cetirizine, because the other form causes drowsiness, so you can have a good sleep. But if you are in the morning, you cannot take cetirizine. It's very difficult to be awake. So it's better to take levocetirizine. Now, next is, I said that how to introduce the concept of planar chirality. Previously, I told you there are four elements of chirality elements: central chirality, axial chirality, planar chirality, and helical chirality. Okay. Planar chirality, I said why it is difficult, because students will immediately ask, how a chiral plane? A plane cannot be chiral. So how do you say that there is planar chirality in a molecule? Okay. And we recently have started on this, that how to introduce. Basically now I am mostly involved in teaching, so having different ways of introducing different topics to the students. Okay. So one is this planar chirality. I said that dimension and chirality, that chirality and dimension has a very strong relation. Like, these are the four elements of chirality. Let's see. Okay. If you look at this chlorine molecule, diatomic molecule, and it's a straight line basically, and this chlorine is only having one dimension, it's a line. Okay. Now if you take the mirror image of this chlorine molecule again, this is the mirror image, it looks exactly the same. Now suppose this chlorine molecule is taken in a one-dimensional world, where only translation is possible, but no rotation is allowed. Okay? So one-dimension world. So the chlorine can superimpose on this chlorine, the other, the mirror image one, very nicely, so no problem. So it is not chiral even in one-dimension world. Chlorine molecule, a diatomic molecule. But if a diatomic molecule is hetero system, HCl, okay, it is also one-dimensional. And if you take the mirror image, now in order to superimpose these two, if you restrict this molecule in a one-dimensional world, you will not be able to superimpose these two. You need a rotation to bring the H on this side. That means you need the second dimension. Rotation is required because only when there is a second dimension available. Okay. So I can say that HCl or any molecule A dash B will be chiral in a one-dimensional world. Okay. And this is what is called a one-dimensional chiral simplex. Sorry. Just a second. I hope this point is clear. Okay. So any diatomic molecule which is heterodiatomic is chiral in a one-dimensional world. Okay. Now if you go to, what happened? Oh, sorry. এখানে press হয়েছে কি? No, sorry. Yes, I think, Abhishek, I will just go back. What happened? Actually, it went to the last. Full screen করে দিতে পারো ওখান থেকে. Right. Okay, similarly, if you take a molecule which is, this is what? This is pyrrole, right? We all know that. Pyrrole is a two-dimensional molecule. It's no longer one-dimensional because it has got a length and also breadth, both. Okay, now if you take pyrrole and take the mirror image of pyrrole, okay, so can you superimpose them? Are they superimposable? Yes, they are superimposable. In a one-dimensional world, are they superimposable? That is the first question. No. In a two-dimensional world, are they superimposable? That means where rotation is possible. So if you rotate it, bring the nitrogen here, so they will be superimposable on each other. So you need the second dimension to make them superimposable. Okay. Now the moment you put another nitrogen, this is what is called imidazole. Then what happens? They are superimposable. They are superimposable by sorry. Only by, if you have to bring this nitrogen here and bring this nitrogen here, they are superimposable only if you take the third dimension. If you take the third dimension, see, rotation can be in plane. Sorry, I have this bad throat. Rotation can be of two. Can be in plane. Is it okay? Okay, now, is it working? Again I go back. First of all, I said one-dimensional chiral simplex, which is a hetero diatomic molecule. It is one-dimensional chiral simplex because you don't allow any rotation to the molecule. It is only chiral in one dimension. A two-dimensional chiral simplex is a molecule like this. This is superimposable only when you take it, you rotate it out of plane and then bring it into the plane. That means 180 degree out of plane rotation, and then they become superimposable. If you don't allow that rotation, then they will not be superimposable. If you rotate it in the plane only, that means in the plane of this whatever projection that we have, they are not superimposable. So you have to take it out of plane and then they become superimposable. So this is called two-dimensional chiral simplex. Okay. So we have one-dimensional chiral simplex, we have two-dimensional chiral simplex. But this loses chirality the moment you take it in the three-dimensional world. Now the next stage is basically the carbon which has got 4 different groups, the molecule that we usually see. That is a three-dimensional molecule with 4 different groups. You don't have the 4th dimension, so you cannot superimpose them on each other. So they are three-dimensional chiral simplex. Remember this. So we have the molecules that are chiral that we deal with today are all, or are being told today, are all three-dimensional chiral simplex. Okay, they are all three-dimensional chiral simplex, and fortunately there is no 4th dimension. That's why they retain their chirality. Okay. Now the question is, suppose, so what is then planar chirality? What it has to do with planar chirality? If you take a benzene ring, and put, say, a chlorine, a X, to the benzene ring, okay, and also 2 oxygens I could see here, 2 oxygens. So if you take these, the question is it a one-dimensional chiral simplex, or 2-dimensional chiral simplex, or 3-dimensional chiral simplex? Can anybody answer that? Or I can, is there any pain here? where I can write? Do you have a pen? এই তোমার কাছে এখানে পেন আছে? Okay. So basically what we are the question was that if you have a benzene ring with a substituent X and two oxygens here, just consider this part, whether it is a one-dimensional chiral simplex. Certainly not, because it is not one-dimensional molecule. Is it a two-dimensional chiral simplex if you have a benzene ring with X and the oxygens at these positions? At these positions, basically what you have to see, that you take the mirror image of this and then see that whether just in plane rotation can allow them to superimpose on each other. That is, page open. দেখতে পাবে কিনা, আলোটা জ্বালাতে হবে। Is it visible now? Okay, so this is the puzzle. These two molecules are mirror images of each other. Are they, is it representing a one-dimensional chiral simplex or two-dimensional chiral simplex or three-dimensional chiral simplex? Can you see it? Is it this is not that dark. আর কিছু আছে? Pen? Can you see it? Is it visible to you? Okay, so give the answer. There is X here, there is oxygen here, there is oxygen here, there is oxygen, there is oxygen, there is X. And this is the benzene ring. So is it what? This is first of all a two-dimensional molecule, so it cannot be one-dimensional chiral simplex. Now the question is whether it is a two-dimensional chiral simplex or not. What is two-dimensional chiral simplex? Which cannot be superimposed by translation and which cannot be superimposed by rotation in the plane of the molecule. The question is now, can you superimpose these two by rotation only? Can anybody answer? Yes. Are they superimposable just by rotation? Just by rotation in the plane? You start rotating. Unfortunately, I don't have the model. If you want to bring this X here, if you rotate this, yes, I think that is much better. If you rotate this, your X will come here definitely, but the oxygens will come at these positions. So just by rotation in the plane, it is not possible to superimpose these two mirror images. Okay, so this represents a two-dimensional chiral simplex. Is it clear to everybody? If you want to match the X, the oxygens will not be in the right position. If you want to match the oxygens, the X will not be in the right position. That's the problem. So that's why this is a two-dimensional chiral simplex. Okay, and but if you have this molecule in three-dimensional world, we have so many molecules. Somebody showed picric acid earlier. Okay, picric acid was shown, but if you take one nitro group off from the ortho position of picric acid, it becomes a two-dimensional chiral simplex. Okay, because the way to find it is basically you look at whether this has a mirror plane or not, a mirror line or not. Actually, it does not have any mirror line except the plane of the benzene ring. So without considering that plane, it does not have any other mirror line. So that means it is a two-dimensional chiral simplex. How they are superimposable with each other? You have to take this benzene ring and turn it upside down. Then they are superimposable. That means you have to use the third dimension. Okay? That is the definition of two-dimensional chiral simplex. Now, if you can stop that rotation happening, that a benzene ring which cannot rotate from this side to that side. That means my hand is tied up in such a way that I cannot rotate it like this. That has to, if you can achieve that, then this molecule will become chiral. And that becomes what is called a planar chirality. And you see the molecule that has been shown here, the same benzene ring with the phenol units tied up with a chain. If you tie up these oxygens via a chain, then what happens? The benzene ring, by rotating, will hit the chain and you can hinder that rotation. Very similar to the biphenyls, very similar. The biphenyls cannot rotate because of the orthoposition, the substituents at the ortho positions hitting each other. Here, the benzene ring cannot rotate because of this chain, because this has hydrogen or X or whatever substituent that will hit this chain. If the chain is very large, then that is not a problem. Then benzene ring can float, can rotate. Okay, that is not a problem. So the chain length is also important. If you have a smaller chain, then rotation is restricted. The benzene ring cannot rotate. Actually, that is the cause of planar chirality. So planar chirality, what is planar chirality then? What we have learned from that? Planar chirality originates from two-dimensional chiral simplex molecules originally, where you have restricted the rotation in the third dimension by putting a chain or whatever. Like these are called cyclophanes. This is called cyclophanes. Here also, because there is a X here, the rotation between the two rings cannot actually rotate in the plane and or cannot rotate upside down. So that gives rise to planar chirality. So again I repeat, planar chirality are molecules which are having two-dimensional chiral simplexes but with restricted rotation. Okay. So what is the chiral plane here? The chiral plane is that two-dimensional chiral simplex when you see it in isolation. So if you look at the textbooks, they will say that this is the chiral plane. This is the chiral plane, but they have not said this, that this is actually a two-dimensional chiral simplex. Is it okay? So that is the introduction of planar chirality, and I believe that this is the way to introduce, rather than saying that it has got a chiral plane, because that gives a misnomer. You have to say a two-dimensional chiral simplex is present, which is having a restricted rotation. Good. The next issue, concept of meso compound. I think previous speaker gave some compounds which were meso. Meso compounds are what? Like mesotartaric acid, we know that is the classic example. Everybody says that it has got a plane of symmetry going through the middle. That means, and it is called also that it is internal compensation, that the top half is exactly the mirror image of the bottom half, and if the top half have plus rotation, the bottom half will have the minus rotation of exact magnitude, and they cancel each other. This is what is called internal rotation. So meso compounds are compounds which are, in spite of having chiral centers, chirality elements, not only chiral centers, in spite of having chirality elements, they are optically inactive. They are called meso compounds, and we say that they are internally compensated. Okay. Now, if I ask you that if I combine a plus molecule and minus molecule through some linker, say plus and minus, will that give rise to a meso compound or not? If I take a plus compound, because you are saying mesotartaric acid can be divided into two segments. One segment is the mirror image of the other segment. So if I now say in the opposite way, that you take the two segments and join to each other, so that should give rise to meso. That means if I take a plus entity and a minus entity of the same molecule and join them, what you get, you should get a meso compound, no problem. On the other hand, if you take the same entity all the time, the plus entity and the plus entity, it's like two left hands. I join two left hands. So that cannot, or that should not give me a meso compound, because both are having the same chirality and both are having the same rotation of same magnitude. So to get a meso compound, you should have a plus and the minus form, and then you join them. Plus and minus form of the same entity, that we have to say. Okay. Now there was a scientist, he died very recently. His name was Kurt Mislo. He was at Princeton University in USA. And he showed that in fact you can take two plus molecules, join them, and you can get an achiral molecule. You can get a meso compound. And the other way, you can take a plus and minus molecule, join them, and then you can get a chiral entity. Just the opposite that what we are saying. Earlier we said meso is basically composed of two entities, one plus, another minus, and they cancel each other. Internal compensation. What Mislo has shown by his experiment, that it is possible to take two plus entities, join them, and get an achiral compound, means meso compound. Okay. What example he took? He took an example which is, this is why I told you to come forward. Yes, just a second. Very good. He took an apple. Everybody knows what an apple does. We are not interested in chemistry of apples. No? If you see a very good apple, we immediately grab it and eat it. But here it is chemistry of apples. That is also kind of a green chemistry, but theoretical kind of green chemistry. This apple, is it symmetrical? Is it chiral or achiral? Means unless you have a very deformed apple. Think of that this is actually a sphere, a good spherical apple. Whether it is chiral or achiral. If I give it to a polarimeter, an apple, will it rotate the light, plane polarized light or not? Thinking that it is a perfect sphere. So it must be achiral. Okay? So it must be basically representing a meso compound. An apple or meso object. Okay? Now so this meso object, if you cut into two pieces, you will think that this cannot be cut into two pieces which are having the same type of chirality, same type of rotation. Means it cannot be cut into two pieces where both pieces have plus rotation or both pieces have minus rotation. Then otherwise how it can be meso? Now what Mislo did, actually this was a very historical thing, that how to cut an apple. You cut the apple or we cut the apple by just from the middle and then go all the way and we get two halves. Okay? But there are other ways of cutting apples into two equal halves. We are not saying that you cut the apple like you cut your birthday cake piece by piece, not like that. You take the apple, you cut in such a way that orthogonal, you take two orthogonal pens. One is up to this, one is like this, another is from the bottom like this, if you can see it. So you take the apple, you cut the apple using a knife, go up to half the point, half of the apple, okay? And cut it also from the lower side and go up to go up to only half. You don't go all the way up. And then you join you cut it from the horizontal position and cut it into two pieces. Basically this will create quadrants. So you join two quadrants, diagonal quadrants, and then that will bisect the apple into two equal halves. So what I said, if I actually cut it already because it will take time also and it is very risky. So go up to this point, if you can see it, and from this way, orthogonal plane, go up to this point, and then join the quadrants. So I just cut from this end and the other end. Okay. So what you will get, you can, if you cut that way, you get two pieces. Okay. Now these two pieces make the complete apple, a meso compound, a meso object. Now what about these two pieces? So this should have plus, if this is plus rotation, this should have minus rotation, or vice versa. But if you look at these two, they are not mirror images of each other. Because it is, if it is plus, if it is minus, they should be mirror image of each other. Right? But unfortunately, they are not mirror images. Actually, they have the same chirality. If you look at this, unfortunately, you are sitting far away. They have the same chirality. I hope this is clear. They have the same chirality. So if it is plus, this is also plus. But so to these two plus entities, you can join and get a meso-variety. This is a typical cut which was used by the French people. You know, French people are very cosmetic in nature. No? They prepare all these cosmetics, perfumes. Their aesthetic sense is beautiful. So we cut the apple straight away. They cut the apple in this way. It's difficult, but they used to cut this apple, and they used to present that, because salad dressings are present in different ways. So they used to cut the apple and keep it in the salad table, on the salad plate. Okay. So this is kind of strange, that same chirality you get from a meso object. How it is possible, whether there is any chemical counterpart of this or not. Okay. Now you can, if you want to, you can pass it on and see it yourself. Better, students, you pass it and see yourself. I have another apple. Okay. I have another apple with me. Now don't eat it. Of course, this is newly bought. Yesterday evening I bought this, okay. So don't come near to me, that is one. And this apple was also bought yesterday. This is the same apple, similar apple, again cut in a similar fashion, but there is a slight difference. I will not go into, you can, maybe the light is better. And what is the chemical counterpart of this? Okay. Yes, right. Now, see, this is the apple cut into two pieces of same chirality, like these two or these two, and then you can actually take objects also. You try this in your home, because apple is costly these days. You don't waste the apple. What you do, take a piece of paper and either circular cut it this way, or, because these are all meso objects, and you can cut into objects of same chirality, which are called homochiral. Have you heard of the word homochiral? That means two molecules are homochiral if they have same chirality. That means both are belonging R family and same type of rotation. Okay. So this is the chemical counterpart. What Mislo did, he took this molecule. You see, these are these two molecules he took. These are what? Mirror images of each other. Just a second. Yeah, they are mirror images of each other, and I'm just checking it. SH and this Br. So when they react with each other, this SH reacts with this bromine and this SH reacts with this bromine, and that gives the meso compound from the same chiral molecule. These molecules are individually chiral, remember. Let me see if I have a better picture here. Yes. these two molecules are mirror images of each other. Both the molecules are chiral. Both the molecules are chiral. Okay, so if this is plus, that is minus. You join these two, you get this molecule, which is a chiral molecule. That means you are mixing plus and minus, and you get a chiral molecule. Earlier example, you are mixing both pluses, and you are getting a meso compound. You see, this is a meso compound which has got a plane of symmetry. I am not going into the very details. I just concentrate on the concept. Concentrate on the concept that if somebody says that can a meso compound be bisected into two homochiral units, that means chiral units having same chirality, same sense of chirality. Yes, it is possible. And that was just demonstrated first in the apple, and then chemically he demonstrated it. That was published in the Journal of American Chemical Society in 1982. So don't have this notion of that it is always internally compensated. Don't have that notion. It is possible to divide a meso compound into only plus entities or only minus entities. And once I thought that this may have some repercussion on the origin of life, because if a symmetric object can be divided into homochiral objects, so there might be some connection between origin of life and this homochirality or the formation of mesoform. Okay. I think just one more issue I want to discuss. This is, I think, a little bit easier. What is the mirror image of an R molecule? What is the mirror image of an R molecule? S, I think everybody will say S. What is the mirror image of S molecule? Everybody will say it will be R. We know that R mirror image is S, S mirror image is R. This is what is called reflection variance. Reflection variance. Have you ever seen that the mirror image of an R center having R configuration remains R in the mirror image? Has anybody ever seen or questioned yourself that is it always true that the mirror image of an R center is S and the mirror image of an S center becomes R center? Okay. So we actually, what happened, there is a series of stereochemistry courses that are all uploaded in the YouTube, whether you have seen it or not. Stereochemistry recorded at IIT Kharagpur. Okay. So there are a lot of questions that used to come in the forum. And one question that raised my doubt about this hypothesis, that reflection variance, that mirror image of R is always S, someone, because it is not identified, who is that fellow, asked me that is it always true that the mirror image of R is always S and S is always R? That is one. And the other is a double bond geometry. You know double bonds are cis or trans. So mirror image of cis, which is Z, remains Z all the time. Mirror image of cis compound will remain cis and the mirror image of a trans compound will be trans. So it is just the opposite. R becomes S, S becomes R in the mirror image. On the other hand, E remains E and Z remains Z. That means cis remains cis and trans remains trans in the mirror image. This is called reflection invariance. That means you are not changing the absolute configurational descriptor during reflection. Okay, this is reflection variance and invariance. Okay. Now I will show you that where it fails. I will show you some example. First of all, it is not always true that the mirror image of R is always S. And also it is not always true that the mirror image of E will always be E and Z will always be Z. Okay. I will just to cut down the time. If I take a molecule like this is a 5-carbon unit attached to a stereogenic unit or a chiral unit, and these are all hydrogens. This is weight, this is weight, this is methyl, this is methyl. Achha, is this compound a meso compound or is it a chiral compound? Who can say that? Is this compound chiral? See, I tell you, nobody is going to describe stereochemistry in such detail. So today you have some opportunity. I am still also very much perplexed with what is there in the stereochemistry textbooks. It's not very easy always to describe things. There are always flaws. You always question yourself that sir is telling this, but you question. So my question is this molecule chiral or achiral? First of all, achiral. Why? Because you think that there is a plane of symmetry, right? That's what you think. Actually, it is a chiral molecule because, yes, because this is CH10 C2H5. So that disturbs that plane of symmetry. So plane of symmetry is not there. This is a chiral molecule, no doubt. Now, if I want you to assign the absolute configuration of this carbon, so what you do? You know that there are set of rules to determine the absolute configuration, and you cannot, like inorganic analysis, you cannot jump to group 4 straight away without doing the analysis for group 1, then group 2, then group 3, A, B, right? You cannot jump. Similarly, in stereochemistry also, while assigning RS or EZ, you cannot jump. You have to first see the atomic number, whether it differentiates the groups. If that fails, go to the atomic weight. Okay? If that also fails, then go to the absolute configuration of those other groups that are attached. And there are rules that R precedes S. You know that R precedes S, and S and also Z. Z precedes E. So if you have two groups here, I am talking about this carbon. So this group is chiral. So this has got S configuration and this has got R configuration. You can do it yourself. And then it is you can differentiate between these two groups because R precedes S. So you have that rule. So you can find out by your priority sequence that this will have an S configuration. Okay. And if you take the mirror image of this is the mirror image of this S becomes R here, this R becomes S here, but this remains still S. If you can do it yourself, go back and then draw a molecule like this. Okay, these are called molecules which are having pseudo-asymmetric center. This is called pseudo-asymmetric center. Why? Because these molecules, this carbon loses its chirality the moment these two have the same configuration. Like the second carbon and the fourth carbon, the moment they have the same configuration, it loses chirality. And when they have different configuration, it will become chiral. So that's why it is called pseudo-chiral system. This carbon contains a pseudo-asymmetric center. Like us, we are also pseudo. We have a pseudo character. In front of our director, we will say sir, and to the students, we will bash at them. Okay. So depending on situation, that is what is called pseudo. Yes, I think your principal is very cordial. Okay, but that is the general notion that we have a pseudo character. So these molecules have a pseudo character, sometimes chiral, sometimes not chiral, depending on whatever is the situation, what are the hands that are. Okay. So you see there are molecules where S can be R, mirror image of S remains S. This is the example. Okay. And what about the, there are so many slides. What about the cis-trans system? I said cis should remain cis. But here you see that if I have this molecule X, which is a double bond, there is X and Y group, and A, there are two A's. This A contains a stereogenic carbon, a chiral center. Suppose it has got R configuration, this has got S configuration, and this X and Y. Forget about this configuration, these are important. So suppose this is always R precedes S, so that will be your 1, and this is your 1, suppose X has higher atomic number than Y. So X will be 1. So this will be what? This will be a Z alkene. If you take the mirror image of this, so this X will be here now S, that will be S, this AR becomes AS, this AS becomes AR. So now this will be 1, R precedes S, and this is 1. So this becomes E alkene. So the mirror image of a Z alkene is becoming E alkene. So you can have many examples. Mirror images of Z changes to E, or mirror images of E changes to Z. Okay, this is called reflection invariance. So I want to point out basically 3 things. One is how to introduce planar chirality, how to the second one is the concept of meso, and the third one is this reflection variance and invariance. Okay, there are lot of rules now we have developed, and that has been published in IUPAC journals. So hopefully we have actually have some knowledge how to bypass this these anomalies, that mirror image of E changes to Z and the mirror image of S remaining S. So how to bypass these anomalies? We have various rules. If you are interested, there are 3 papers now that have come out. I don't actually, yesterday night I prepared these slides. I don't have the references right now. You can write to me, or I can give it to Abhishek, the references where these are published, and hopefully those will be the new set of rules, because the main culprit for this R not becoming S in the mirror image is the rule R precedes S. That is the main culprit which is causing this situation, and that is causing lot of misconceptions in the mind of students. Okay. So hopefully some glimpses of chirality. You see, you might be thinking that I know many things about chirality, but there are always gaps in your understanding, in my understanding also. Because this, whatever I have presented, this is, I just realized in the last 3-4 years, that there are deviations from what are considered standard truth in stereochemistry. So I end here. This is presently I am actually the INSA senior scientist at ISA Kolkata. So that acknowledgement is there, IIT Kharagpur, ISA, and this is my student who actually also helps me in drawing these and discussing all these things. We have many more anomalies we have discovered in stereochemistry. So slowly that will come one after another. Prabhuddha Ache, yes, Prabhuddha, you know, he is in a college near Birati, exactly. Now, concluding remarks, this is mainly for the teachers. That stereochemistry, we should stress the importance of stereochemistry, because it is directly related to life. That is number 1. And the third, appeal to academia. This is our appeal, because these days our well-known stereochemists are not there. Professor Noshipuri is no more. Professor Talapatra is also more than 90 years old. And after that, Subroto Sengupta, he wrote a very nice book. He is also not very well. And very few people are there who are dealing with research in stereochemistry. Okay. So appeal to the academia that to provide more space for chirality. Because at IIT Kharagpur, I said that there should be some advanced course on stereochemistry. So there are always differences. Teachers say that what is there in stereochemistry? It is only RS, nothing there, nothing more than that. Okay. So that sort of mentality should go. because we are guided by chirality. You always should know that. Call upon the teachers to empower the student community with chiral science. And there is a phobia about stereochemistry, which is called stereophobia. So you should come out of this stereophobia and study stereochemistry. Always question yourself. When a teacher says something, you said, sir, are there any violations of the rule? Are there any violations of your pericyclic reaction rules or not? You know whether there are violations. Whether you read pericyclic reactions. You must have read Woodward-Hoffman's rules, all these things. Okay. Are there any violations? People might ask. Similarly, stereochemistry is there. So you should come out of stereophobia. And our duty also as teachers to reduce that gap between our understanding of stereochemistry and connection with the chemistry or biology. Okay? I think that is the last slide, and thank you. If there are questions, you can ask. Is it for me? Yes, sir. Yes, I think whether actually after I started my journey in the morning, I had two models, very nice riding models. I thought in the night that I will take those models. It would have been nice if I had taken a model and show it to you. But without model, the thing is that not everybody has access to the model. And that's one reason why stereochemistry is not very appreciated. Because it's it's a conceptual subject. You have to think virtually. But today you have computers, so you can draw molecules showing in 3 dimensions, like ChemDraw. There is Chem 3D programs where you can draw molecules in 3 dimensions. But your question is, yes?
No, my query is, see, in group theory and symmetry, there are many mathematics. This chiral, etc.
Exactly, that is another, see, chirality, I said the importance of chirality, I mentioned only about biological molecules, biology, molecules, the origin of life and all those things. But there are other things, like Professor Sinha is saying about group theory, which is directly connected to your spectroscopy now. So that is another part. I didn't mention that. Thank you for mentioning that. I forgot that its connection with spectroscopy, group theory and spectroscopy.
Thank you.
Any other participant, student?
কোনো প্রশ্ন আছে
Have
কি?
we any question?
থাকা উচিত তো, ডায়াল করছে না।
কেউ ডায়াল করছে না স্যার।
হ্যাঁ?
So, question.
He has come out of stereophobia. Yes, come here.
হ্যালো, বলছি স্যার যে আমরা যে বাজারে গ্লুকন ডি খাই, ডি ডেক্সট্রো রোটেটারি,
এই
তো এল গ্লুকন ডি খাই না কেন?
গ্লুকন ডি, ডিটা দেখেছো কি লেটারে লেখা থাকে, whether it is capital or
বড়
small?
বড় হাত,
হ্যাঁ? Small or capital? কিসে লেখা থাকে?
ক্যাপিটাল।
Capital D, right? Capital D does not mean dextro or levo. Remember that. It is only small d or small l. So you have to go even fundamental things, the nomenclature system. Capital D is basically the last, that means the C5 carbon. If you know the structure of glucose, the C5 carbon, which is on the right side, if it is drawn in the Fischer projection formula. And Fischer gave this name, capital D. If the weight is on the left, then it will be L. So when you say glucon D, you have glucose in that is D, capital D glucose. Okay, so it is not dextrorotatory. It may be dextrorotatory, that is a different thing. But that D does not define that it is dextro. So remember the difference between capital DL versus small d, small l. Small d is dextro, small l is levo. Capital D and capital L are absolute configuration of the last chiral center in glucose. Last means the C5.
Thank you.
Good afternoon, sir. Sir, let's just think we take a solution of a chiral compound and passing a polarized light to the compound. And we may see it may be rotated either in clockwise direction or in anti-clockwise direction. So what is actual the thing occurred in the compound? Why is the light rotate in clockwise or anti-clockwise direction?
Why it is rotating?
Why actually
Okay.
this happened?
I think maybe that is advanced stereochemistry code. That what is the origin of this rotation? That
Yes,
is
sir.
your question. Okay. Now suppose you think a carbon with 4 different groups. Take a very simple system. 4 different groups. These 4 groups have different polarizability. You have heard of polarizability? Polarizability. We'll have different interactions with this light going through it. All these 4 groups, okay? And the plane polarized light is basically composed of 2 components. One is left, at least that is composed of circularly polarized light. One is left circularly polarized light, another is right circularly polarized light. And to make it very simple, think plane polarized light having 2 components. Okay, a left component and a right component with equal intensity, with equal velocity. Okay, it goes through a chiral system. Now what happens? Because of the chirality, one of these, either the left or the right, one of these circularly polarized light will become slow, will travel slower, or the other ones travel slower. Okay, 2 things can happen. That depends on refractive index. You have heard of that Snell's law and all those things, refractive index. So velocity of light depends on the refractive index. Okay. So when it goes through a chiral medium, what happens? The left and the right have different refractive indices, okay, as it goes through the medium. So one becomes faster, another becomes slower. That is one effect, okay. And that gives rise to what is called rotation, because if you have 2 equal arms, and if I draw the resultant of these 2 components, it will always be in vertical, right? The moment one becomes shorter, another remains the same. So what will happen? So your resultant will shift either to the left or to the right. Where is that? What I am saying, this is the, not this one. Okay. So these are 2 vectors representing the 2 circularly polarized light. So initially they have equal speed, equal intensities. But the moment one slows down, then what will happen? It will not look like this. One will be like this, another will be, sorry, one moves faster, one moves faster, another moves slower. So what will happen? When this arm is here, this arm may have moved faster and come here. So what will be the resultant now? It has now shifted. Okay. That is the reason that why you get rotation. So it all depends on the velocity of the 2 circularly polarized light, which makes the plane polarized light. If the left moves faster, it will be levorotatory. If the right moves faster, it will be rotating.
Thank you, sir.
Yes? A chiral molecule is always. Now theoretically, as I said, it is a 3-dimensional chiral molecule. So if I have a 4-dimensional world, it will lose the chirality. But that is virtual. A chiral molecule is always chiral unless you do some chemical reactions. So you can do some chemical reactions to destroy the chirality. Now your question is whether it will always be chiral. It will always be chiral definitely unless you subject this to certain chemical reactions. Yes, chirality and asymmetry. See, that is another confusing situation we have created. We organic chemists have created.
but
They are same actually. Asymmetry. If I say a molecule is asymmetric, that means it is chiral.
But sir, in the world we like to be symmetric world, sir. But you can tell the chiral is the important thing.
We
in
like
our life.
symmetric world because it looks beautiful. Huh?
Yes.
But it is made up of chiral molecules. You take chiral molecules, our body is almost symmetrical, right? Almost symmetrical, because, but it is made of chiral molecules. I showed you that the concept of meso, that we can have plus and minus combination and then make it symmetrical. Okay, that makes it. But always, not always symmetrical things are beautiful. If you have seen Satyajit Ray have an artist name.
Yes.
Huh?
Of course.
So go and see his Charulata, okay, famous movie. And it was, the heroine was Madhuri Mukherjee. And he, to symmetrize the face, he deliberately put a dark spot on one of the cheeks and not the other, to look it more beautiful. So the way you look at it, but mostly it looks symmetric, but inside it is all asymmetric. Yes. Yeah, that you can apply. Same complex. Your metal complexes, like your first chiral complex was this triethylene diamine, what was cobalt something, that was the first one. So the same rules will apply. However, you have to be careful. If you go to the octahedral system, your all theories for the tetrahedral system may not hold. You have to devise new rules, because we are always dealing with the tetrahedral system. So
Sir,
the concept of pseudoasymmetry.
I have a question, sir.
Yes.
Sir, how we can check the pseudo-asymmetric center at a glance?
At a glance. At a glance, yes. You look at the system. First of all, it should have pseudo-asymmetric system should have odd number of carbon atoms. Odd number. Okay, if it has 2, then it cannot have a pseudo-asymmetric center. It should have odd number, okay? That is number 1 point. Then the upper half must find out the middle carbon, because if it is odd, there is a middle carbon. See the upper half and the lower half. Are they look same? That is number 2. And number 3, whether the configuration of these two halves are R and S or S or R. Okay, then that becomes a pseudo-asymmetric center. Is it clear?
Yes, sir.
More or less. Yeah. I think some stereophobia has gone. Once one fellow asked certain questions, so they started asking. If you have any questions, you can always write to me. But I will, Abhishek, I will send those references, the papers that we have published on the pseudo-asymmetry as well as the reflection variance invariance, and the third one is the how to introduce the planar dimension based. Okay. Yeah,
Thank you, sir,
but he debe
for your nice and beautiful lecture.
Thank you so much, sir, for this wonderful session. We are highly delighted with your valuable knowledge you have shared with us. Now we will have our lunch break and poster presentation by UG and PG students. Please collect your lunch from the canteen building. Then we will return back with our technical session 5.
worked as a lecturer in Burdwan University also. He have a good publication, around 480 original research publications, and awarded 53 PhD degree and supervised more than 22 research projects. He get different type of recognition from the different institutions and other industries. He get different type of academic awards like West Bengal Academy of Science Technology, elected Fellow Engineering Science Society, Fellow of Royal Society of Chemistry, and he visited different parts of the world like Taiwan, Japan, Singapore, Italy, and he get engaged in different editorial board like Inorganic Analytical Chemistry, Journal of Indian Chemical Society, Chemistry and Indian Journal, and other journal like Organocatalysis of Bentham Science, Associate Editor of Current Microwave Synthesis, Bentham Science, former Honorary Secretary of Indian Chemical Society. At present, he is the Secretary of Indian Photobiological Society. For this session, sir, I invite you to give your valuable lecture.
Hello. Good afternoon, friends, and also I must thank the Professor Hassan for introducing me, and also in the last lecture Professor Bausak is here, and we had a very wonderful and thoughtful scientific talk. And in my topic, so already you see this one, the hybrid materials, some of their applications towards sustainable society. And hybridization is well known to us, both in chemistry, physics as well as in biology. So the same meaning is extended to the material. That means if I ask what is material, who are the materials? The materials are also the chemical compounds. Those have some application potential. Societal application either in biology or in any other area, then they are the materials. For example, see cisplatin. This is a complex compound, very simple complex compound, but it has anti-cancer property and it is very useful drug. So it becomes a medicinal material. In that way, hybrid material means more than two or more than two molecules are mixed together. Either they are being physically or some chemical interactions to give you that similar type of system. So there are applications towards sustainable society. So hybridization, this is very well known to us. Sukumar Rai Abul Tabul, Hans Zaru. All these pictures, এই ছবিগুলোই আমাদের বুঝিয়ে দেয় যে হাইব্রিডাইজেশন কি জিনিস। হাঁস ছিল সজারু, ব্যাকরণ মানি না, হয়ে গেল হাঁস জারু কেমন তা জানি না। Very wonderful every line. That gives you the concept of hybrid animals. Today it is well known to us. বাংহ, বাঘ এবং সিংহের যে হাইব্রিড। And these are also make hybrid system, good listener and good writer. For a teacher, the teacher has to be a good student. Otherwise, the person cannot be a good teacher. So today who are the students, they will be a good teacher in society if they listen, they write, and they interact with the teachers. And today during our lunch time, we heard from Professor Bosak, তাদের সময় ক্লাস 8-এ তার ছাত্র বন্ধুদের সঙ্গে তিনি খুব ভালো ছাত্র ছিলেন, তো সেটাও একটা ওই ধরনের যে গুড টিচার অলওয়েজ in his student life he was a good student. Hybrid material. In practice in chemistry, the hybridization means organic and inorganic. Herein we are talking about the hybridization, means one part is the organic, another part is inorganic. Although this compartmentalization of the different parts of chemistry, they are the fullest concept. This is organic, he is inorganic, he is physical, he is analytical. This is a foolish concept, but we need to develop holistically, considering that concept of mixing by organic part and inorganic part. Polymer, organic group is there, and there in the metal ion. And there are commonly two ways of the classification. One is the physical interaction, other is the chemical interaction. That is the two parts. One is the inorganic part, other is the organic part. They may interact physically or chemically. And one of the interesting hybrid material, permutate. Very well known compound, silicate compound that is naturally available and for the water filtration. And the water from the surface level percolates to the ground level, recharging takes place, and the purification causes on the silicates. By silicates, that is the permutate. And the concept of coordination chemistry, in fact, is the basis of the foundation of the coordination polymer, or today very well known terminology, the metal organic framework. That is, organic frame is there, metal is, and in coordination complex, one is the central is the metal ion, which is being bonded with some ligands. It may be organic or inorganic. So we are talking about the type of ligand which acts as the bridging group. The students, I think the azide, thiocyanate, acetate, they can bridge more than one metal center. So they are the bridging ligands. Bridging ligand brings two metal centers very close to each other, so that the metals can interact themselves. Metal orbitals can interact, or metal can communicate the electron from one center to another center through bridging communication. And this communication may be carried out through bond and through space. So coordination polymer, as you know, coordination chemistry started by Alfred Werner, and he received a Nobel Prize in 1913. And then coordination polymer, first coined by J.C. Baylor in 1964. And today there are varieties of coordination polymers, and Professor Bosak told you the 1D, 2D, 3D. In case of the coordination polymer, since polymer, one-dimensional polymer, that is propagation in a single direction, two-dimensional polymer, it propagates in two directions, and three-dimensional polymer similarly. And this propagation leading to the coordination network. And this coordination network develops some varieties of structures as well as structural feature leading to the formation of the cavity. And this cavity, for example, you see herein, this one, see these are the cavities herein. But in one-dimensional part, either in zigzag fashion or in linear fashion, there is no some cavity. While in a two-dimensional part, that is the planar, while the three-dimension, they have the cavity. And this cavity is a very interesting part, and I don't have that idea about the symmetry of the cavity, and what Professor Bosak told you, the chirality in the molecule. Today people are now designing metal organic framework with chiral cavity. And this chiral cavity is useful for the synthesis of chiral molecule where they are serving as the catalyst, or as well as the separation, chiral catalysis, chiral synthesis, all sorts of being carried out by chiral cavity. And this cavity, pore size of the cavity, pore symmetry of the cavity, they are very important part. Pore symmetry. You know, pore symmetry, pore is not at all only spherical. See, this is a spherical pore, but if it may be a triangular one, so the pore symmetry has changed. That pore may be a square plane, maybe rectangle, or any other. So pore symmetry, that is very important to separate different types of symmetry-based materials. So the metal organic framework has the interesting property. In catalysis, you know, this pore acts as the pot, for the catalytic pot, where the reaction can be selective reaction, very selective reaction that can happen. So the formation of the chiral cavity is one of the very important tasks of the metal organic framework. And what's the difference between coordination compound and coordination polymer? I think you can understand. The ligands, those can bind more than 2 metal centers, they form the polymer. That means extending in both the directions. And then coordination metal organic framework, they are also coordination polymer, but the difference is that metal organic framework has the permanent cavity. And this cavity have different symmetry as well as cavity has the flexibility. Cavity may be rigid, cavity may be flexible. For example, permutate, having the silicate cavity, they are the rigid cavity. That's why they serve as only to pass sodium ion and proton. You just remember your pH electrode. That electrode does not work in the solution of calcium hydroxide or cannot work in the solution of lead hydroxide. Since all they choke the cavity, that is permanent. Porosity is fixed. Now interesting part is the flexible cavity. And this flexible cavity, sometimes this flexibility is stimulated by the external forces, like heating. Heating may change the flexibility of cavity, cavity size, cavity symmetry, cavity activity. Besides the cavity dynamic character of the cavity, dynamic porosity, what is known as dynamic porosity. That means depending on, say, our belly is not fixed in size. It can expand. ভাত খাওয়ার পরে অনেকটা ফুলে যেতে পারে, তাহলে দ্যাট ইজ ফ্লেক্সিবল। তুমি খাওয়ার শেষের দিকে আবার যদি দুটো রসগোল্লা আসে, খাওয়ার ইচ্ছে নেই, গলা পর্যন্ত এসে গেছে, তারপরেও ঢুকে যাচ্ছে, তাহলে দ্যাট ইজ ফ্লেক্সিবল ক্যাভিটি। সো দ্যাট ফ্লেক্সিবিলিটি ইজ ভেরি ইম্পর্টেন্ট। দ্য ডাইনামিক ফিচার along with flexible feature. That is same material, same metal organic framework can have the varieties of applications if it is dynamic in nature. মানে একই মলিকুল স্যার যেমন দেখালেন আর এবং এস, আর অ্যাক্টিভ হচ্ছে, এস ইনঅ্যাক্টিভ হচ্ছে, আমার যদি ওই রকম কোনো ক্যাভিটি থাকবে যে শুধুমাত্র আরটাকে আইসোলেট করবে, যেমন ধরো অ্যাসকর্বিক অ্যাসিড ইন নেচার আইসোলেটস অনলি এল, while in laboratory you cannot isolate that, it will be in racemic form. কিন্তু আমার যদি এরকম কোনো মেটাল অর্গানিক ফ্রেমওয়ার্ক আমি ডেভেলপ করতে পারতাম যা শুধুমাত্র এলটাকে বার করে দেবে, তাহলে আমার ল্যাবরেটরিতে তৈরি করা অ্যাসকর্বিক অ্যাসিড ক্যান বি সেপারেটেড কুইকলি। সো দিস ইজ দ্য অবজেক্টিভ ফর দ্য ডিজাইনিং অফ different types of metal organic framework. On the other hand, they are very stable. Since metal bonded with ligand, they are very stable, very low solubility, thermally also stable, optically stable. On the other hand, in optical stimulation, thermal stimulation, magnetic stimulation changes the symmetric characteristics of the cavity. So there are the different characteristics of pores. They are the persons who are responsible for supramolecular chemistry. Supramolecule. Atoms makes molecule, molecule makes supramolecule. What's the difference between macromolecule, polymer, supramolecule? That is a very fundamental question. In supramolecule there are also bonding forces, supramolecular forces, If you go through the books written by Linus Pauling, Nature of Chemical Bond, there you will find and different types of non-covalent interactions like hydrogen bond, CH pi interaction, pi-pi interaction, halogen-halogen interaction, sulfur-sulfur interaction, all these are sorts of weak interactions unite the molecules. And this union of the molecules through some supramolecular forces make them supramolecular system. And the supramolecular chemistry, the chemistry of the intermolecular bond covering the structure and functions of the entities formed by the association of two or more chemical species. They received the Nobel Prize in 1987. And these are the different types of supramolecular interactions. And interaction type is very important. And these three people received Nobel Prize because of use of these supramolecular forces, hydrogen bonding, in the form of the different types of mechanical movement. This is well known to you in DNA structure, the tertiary structure of DNA. There are different types of hydrogen bonds leading to the DNA characteristics, which is the information transferring agent, and that information transfer goes through hydrogen bond. If that hydrogen bond is somehow corrupted, then DNA will corrupt. That's why the radicals are very dangerous to human health as well as to environment. Since these radicals attack DNA along with oxidizing agents, for example nitrous acid, nitric oxide, what we are inhaling in our laboratory, all these are dangerous. Halo solvents, they are dangerous. Since they produce this heavy elements like lead, arsenic, mercury, why they are so toxic? Because they bind the heterocyclic bases constituted DNA. And once that hydrogen bond breaks or weakens, then the information transferred to the next progeny will somehow disturb, and that causes the genetic disorder, genetic disease, etc. How this metal-organic frameworks of the coordination polymers are prepared? There are many methodology, not going to the detail of it, and the application potential of this metal-organic framework are huge. Gas absorption, storage, gas separation, electrical conductivity, catalysis, etc. And now the question is, what's the application of this metal-organic framework or coordination polymer in the sustainable society? What sustainability means? Today, you know, by 2070, government of India will stop the use of carbon fuels. To sustenance of life on the earth, this earth, a green earth, is turning to brown because of human activities. And to reduce the carbon emission, scientists are trying to generate materials which can generate energy out of carbon, not using carbon, or can be used, but somehow it will be reused repeatedly. For example, in this room there are huge number of lights. You know, there are about say 60 bulbs are there, 60 points. If you illuminate this room by 60 points, then you just calculate what's the amount of energy will be consumed by this room. If it illuminates for 1 hour, then huge amount of energy will be consumed. But if you have only one bulb which can illuminate with equal intensity, then certainly it will be of useful, and it will, along with healthy, it is economically beneficial. That how can you done it? You can do it by just painting fluorescent color, and that fluorescent color will repeatedly reflect the same light, and thus the room will be illuminated with equal intensity. So today's CFL, that also reduces power consumption. On the other hand, fluorescent color on the wall, that can decrease the amount of light necessary for illumination. So this is one way to preserve energy, and another way to preserve energy is to develop, for example, you know, piezoelectric material, pyroelectric material, and today people are going to, it will come to market quickly, যে তোমার মোবাইলটা তুমি যদি মাথায় ঘষে নাও তাহলে মোবাইল চার্জ হয়ে যাবে। দ্যাট মিনস সো পাওয়ারফুল technology is now designed. How can you identify this metal organic framework of the coordination polymer? There are all the techniques, all sorts of spectroscopic techniques can be used for your identification, not going to detail of it. This is one very interesting example for the manganese 2 having 5 unpaired electrons. It is bridged by azide. There are 2 different types of bridging. One is, you see, this is 1-3 bridging, this is 1-3 bridging, other is 1-1 bridging. These 2 bridging, this bridging 1-3 bridging is antiferromagnetic, while 1-1 bridging is ferromagnetic. And its magnetic property, you see, there is a very interesting magnetic property change. At low temperature, it becomes ferromagnetic, while at high temperature, it becomes antiferromagnetic. And that magnetic change, because of its change in the structural feature at low temperature. And that structural feature is leading to a special type of magnetism, this is remnant magnetism. The electronic spin, the spin those are parallel or anti-parallel, but under a strenuous condition, the spins do not follow the parallelism. They are either parallel or anti-parallel, they are rather inclined at an angle. This is because of the structural strain developed at low temperature, and that is the reason for this remnant magnetism. These are the interesting quality comes because of the giant structure. So metal organic framework brings you, or coordination polymer brings you this property. Not going to the detail of all these. Okay, we in our laboratory what we are doing? We are the inorganic chemist. That is, we are designing some organic unit and then bind with the metal ion. That is our main purpose. And the binding of the metal ion, since we are going to develop the polymer, so our designing principle will be also similarly, so that it can bring more than 2 metal centers together. Herein, our bridging molecule is this one, dicarboxylate. I told you the carboxylate can bridge the 2 metal centers, or more than 1 carboxylate can bind the 4 metal centers together. Herein this is a bridging agent. Another molecule here, this is imidazolyl phenyl azoimidazole. This is our molecule what we have designed. Very simple molecule, and it undergoes cis trans isomerism. You know the photochromism. On light radiation it changes its color. And this color change because of the change in the structure. This trans structure has one color, cis structure has another color, and that we follow by spectrophotometric process. Okay, this is one thing. But what is our observation in metal coordination polymer, where the carboxylate as well as azoimidazole present? In case of zinc complex and cobalt complex, in zinc complex, it is zinc complex, the azoimidazole, azo bond remains pendant, free. Phenyl azo is free. So it undergoes this photochromic transformation, and this photochromic transformation, it is observed by all sorts of spectroscopic routes, not going to detail of it. An interesting part is its helicity. What sir told you, the helical geometry, it is the arrangement of the atoms, arrangement of the groups, that gives you this helicity. And this helicity, in fact, brings in this molecular unit, you see this one, here in this pattern, or this is in this pattern. So this patterning of the bridging groups, this patterning of this bridging group, that is interesting. And this brings you the property, interesting property in the molecule. Okay, one of them is this photochromism, and you can see it change in color from light yellow to brown. It is because of this photochromic transformation, and photochromism is well known to us since we are wearing photochromic glass. Photochromic glass to protect our eyes. There are different ways why the photochromic glass, how it serves. Like there may be redox active agent, or maybe photochromic agent that changes its structure, and so on. And this photochromic behavior in our system, it is very stable. You see, after repeated irradiation that is observed in the organic molecule, commonly repeated irradiation leads to the photodegradation, photodecomposition. That will unstable the material. While in case of the coordination polymer, because of the metal center, the photodegradation is stopped. And you see the repeated irradiation, the intensity of the band, intensity position remains fixed. That means the molecule is very stable towards the, that is one of the important aspects of the sustainability. So you will design a molecule that can be repeatedly used. Even after repeated utility, it does not change its activity. It will continue for infinite time. Okay, this is another way by which you can repeated irradiation at very short wavelength. It becomes the azo group clips and the radical forms, that radical is observed and the permanent change. Okay, we design another molecule. Herein you see the cavity. In the cavity is generated. In the cavity, solvent molecules are placed, and on heating that solvent molecules are evaporated and vacant cavity generated. Interesting part is here, the vacancy when generated, you can think that the overall structure may collapsed. That is the flexibility part. Although you release H2O, water molecule or DMA from the cavity, but the overall molecule remains unchanged. That is, structure does not collapse. So the activity that can be used for another function. That we did. That this cavity is useful to absorb iodine molecule I2. You know, iodine is very important since it is also radioactive iodine used for thyroid treatment, as well as that's why iodized salt we are taking because of this one. So iodine purification, iodine isolation, iodine adsorption, that we can do, and that is we did it by, you see, this experiment can show you. This is our iodine uptake gradually in start solution. Say blue intensity gradually decreases. Herein the iodine starch solution. Okay, iodine is there along with starch, so it is blue, and we add our material. Then this material takes iodine from starch, that's why the color intensity gradually decreases. And whenever that iodine which is absorbed by our material, that iodine again releases. Herein you see the iodine releases. Iodine released in ethanol solution. So that means you can regenerate your material and for repeated iodine separation. And after iodine absorption, it has changed its activity, particularly the conductivity. Our objective is to utilize or to develop a material that can show the multiple activity. One of them is the iodine absorption, other one is its electrical conductivity. Not going to the detail of it, you see the electrical conductivity of this material. Electrical conductivity of this material. And here in the current voltage diagram, Tux plot can show you the energy of the band gap energy in experimental band gap and theoretical band gap. And this molecule shows very interesting conductivity. You see, on light radiation its conductivity is enhanced, and after iodine absorption its conductivity is again increased. So the molecule itself is conducting. After iodine absorption its conductivity is increased, and on light radiation the molecule enhances its conductivity. See, our objective is to utilize the solar radiation to improve its conductivity so that the energy transfer can be possible. So this molecule shows the varieties of activity. And superconductivity, another interesting part. Superconductivity means, conductivity is the reciprocal of resistance. So increase in conductivity means decrease in resistance. Superconductivity means zero resistance. So you have to make a material that could have zero resistance. Zero resistance means your electricity will conduct without adding any energy, without there is loss in energy. See, if your thermal power plant produces 100 megawatt power for your area. So your area is fully consumed that full amount of 100 megawatt. But if you count the consumption of current in your area, then you can find the sum of the consumption becomes 80 megawatt. Where that 20 megawatt current goes. These are the transmission loss. The transmission line through which it is coming, there is always, because of resistance, heating takes place. The objective today is design metallic, substitute metallic wire by molecular wire. This molecular wire, where it is polarized, already electrons are in order. Resistance is zero. So there will be no energy necessary to bring electrons into the single direction. This is the concept of superconductivity, what Kamerlingh Onnes first proposed in 1911 and received Nobel Prize also. And the idea of superconductivity is related to Meissner effect, that is during superconduction, magnetic field becomes zero inside it. Magnetic field zero means the electrons are in regular phase. And there are many concepts of it, particularly in the crystalline state, where the electrons and holes, they will be together, and hole will move one direction, electron will move another direction. That is the BCS, well-known BCS theory, and they also received Nobel Prize. And you know, in 1986, very simple compound, these two people designed, synthesized, a physicist, they are the physicists, Bednorich and Muller. They synthesized one mixed oxide, lanthanum, barium, copper oxide. Objective is the same, to generate superconductor. That is conductivity at room temperature. Commonly Kamerlingh Onnes shown mercury as superconductor at very low temperature, at helium temperature, 4.2 K. But to bring that low temperature, it is again costly. So it has to bring into the room temperature superconductivity. And they synthesize this lanthanum, barium, copper oxide, varieties of barium copper oxides, those are showing the superconductivity. And these materials, these oxide materials, have some problems. Problem means degradation. Structural degradation, they are not flexible. So the molecular chemist then targeted to design molecular material. There are coordination complexes, those can exhibit the superconductivity. Because of their structure, the electrons become regularly arranged. One such example, there are different molecules we have synthesized by terephthalic acid, by this acid, this acid, etc. And all these are showing different structural geometry, and they have the band gap which is about to semiconducting band gap. And the semiconducting band gap, as you know, the semiconducting band gap, it is up to 5 electron volt as a energy gap up to 5 electron volt. Beyond that, the electron cannot be transferred. So 5 electron volt, this band gap, here in our band gap is below 5 electron volt, so all they exhibit the semiconducting property. And we determine the semiconductivity and current voltage diagram. You see, up to 1 volt almost, it follows current proportional to voltage. That is Ohm's law. V varies as I. That is Ohm's law. That Ohm's law follows up to that. And after that, if you increase voltage, then you see there is sudden upsurge of current. And the current potential relation becomes V varies as I square, V varies as I to the power 2.5, 2.6, etc. That means current is hugely increased. We are in fact in the sustainable development program, we need it. That is, small change in voltage can generate huge current, then certainly the energy crisis can be tackled. That is our objective, to generate the material which will show the very high amount of current, even using light as radiation. And see, Nyquist plot can give you this information. Those have the lower base, they are the good conductor, and those have the higher base, they are the bad conductor. From that Nyquist plot, easily you can utilize it. Okay, we designed, our objective is to use the molecules to make these materials. Those can have the conductivity as well as some other material property. Herein also some other molecules we have designed, and they are also showing the similar type of property. You show this is also same one. The molecules are showing this conductivity, high conductivity at higher voltage, and the reason is the same. Here in the cadmium complexes, they are also showing similar behavior. Interestingly, this material shows conductivity along with the chromium sensing. Sensing is another application. See, we design material not only for the execution of only single property, multiple property. That is the objective for sustainable development. So this material shows chromium sensing property also. And chromium, you know, is very useful for health, since chromium controls the glucose tolerance limit. Glucose tolerance limit in biology is regulated by chromium. Again, potassium dichromate is huge amount used in laboratory as well as in the tannery industry. And tannery industry, in fact, the effluents coming from tannery industry contains huge amount of chromium 6. That chromium 6 causes varieties of problems including cancer. So chromium detection in our drinking water or foods is very important. That's why we designed this molecule to examine this chromium sensitivity. Here in another molecule you see, this molecule has a thiosalicylic acid, and this molecule has interestingly undergoes the sulfur-sulfur bond formation, disulfide bond formation, which is very common. When sulfur is exposed to air oxygen, it will oxidize, giving the disulfide. And interesting part of this molecule, you see, this is the molecule that has the sulfur-sulfur bond, and this molecule undergoes on light radiation, its sulfur-sulfur bond clips. Herein this is the model, this is the position where sulfur-sulfur bond forms, and this sulfur-sulfur bond clips. Not only, and this clipped bond again rebuilded by air oxygen. That means it clips by light, and by air it again regenerates. And this is very important, particularly if you make a material that can regenerate its regeneration of the same one. That is very useful for several times of use. That happens herein. So reversible polymerization of the sulfur-sulfur bond, and cleavage can be done by redox pathway. You can reduce by giving electron, that can also be generated. Okay, this molecule also shows this conductivity. Not going to talk all these things. They are also showing conductivity, different conductivity, and you see this current voltage region, this current voltage plot. This is one type of plot, this is another type of plot, and this relation, say I variegated, V variegated, I square, this relation, say V variegated, I to the power 2.5, and so on. That means under different voltage strength, they have the different activity, and this activity is coming by changing the nano size of the material. Thus, the mechanistic part of the voltage change in this part and in this part are different one. Not going to the detail of all these things because burden to students. Okay. You see, this is another one, and that has also the different cavity size. This topological structure you see, by changing on metal, zinc and cadmium, you see the structural topology, how it changes. Not going to the detail of the coordination, etc. You just look into this topology. Yeah, this topology is polycatenated square grid, and this topology is diamond-like. Okay, not going to the detail of the nomenclature of this topology. Just look into this figure. This topology has a large cavity, but this topology does not have cavity. That's the reason the conductivity changes, and this zinc and cadmium, you know, cadmium has a 4d orbital. So cadmium larger d orbital has a better flexibility, so the electronic repulsion is less. That's why the cadmium complexes are showing the larger conductivity than zinc. That we also observe. Okay. This is another one, let me to tell you, interesting one. Along with the conductivity, this molecule shows, herein you see one carbon-carbon double bond, naphthyl vinyl pyridine. This is a vinyl group carbon-carbon double bond and distance is around 4.09. And on light radiation, this carbon-carbon double bond undergoes pericyclic reaction, CC coupling. You know, sir told you the light reaction, the carbon-carbon double bond can couple, giving you the carbocyclic product, and that carbocyclic product generates polymer. This is a monomeric system, and this monomeric system or light radiation generates polymer. So light is the agent to form the supramolecular system, and this molecule also exhibits the varieties of conductivity. Here in the sensing property, this molecule shows iron, aluminium, chromium sensing. They have the different sensitivity. So the polymer can have the property like sensing, property like conductivity, property like SS bond formation, and all these, along with their antibacterial, antimicrobial activity. The molecules you design, the molecules have some biological influence. Since the coordination polymers, they are very stable under the blood pH or even higher pH or lower pH, say pH 1 to 12. Within this range, they don't have any structural deformation. That is checked by this powdery study, etc. And they are showing the very interesting antimicrobial property. And we have studied this antimicrobial property as well as anti-cancer property using different cells, HeLa cell and so on, and they are showing the anti-cancer activity also. Okay, this is another one with the zinc complex. They are showing the same conductivity as well as anti-cancer property. And here in very interesting part, cadmium complex C, the one macrocycle is formed, metallomacrocycle, and on this, because of this macrocycle, the flexibility comes. That means you are going to design molecules of the different structure, different flexibility, different geometry, and this geometry in fact inputs different property, and all these property are examined in this case. And here in one interesting property, this is a very interesting molecule. You see, this is the magnetic plot, magnetic moment with temperature. With increasing temperature, the magnetic moment increases and then decreases. While in that case, in this molecule, the magnetic moment increases. So it becomes ferromagnetic at higher temperature. This molecule shows the ferromagnetic at first phase followed by antiferromagnetic. All these two compounds are copper compound. One copper compound is tetranuclear, other compound is binuclear. Tetranuclear complex that shows this ferromagnetic behavior, and binuclear complex shows this antiferromagnetic behavior. That means magnetic property changes with the number of metal centers in the polymer. This is also another molecule. This molecule shows the carbon dioxide reduction. You see, that is present day research is going towards this direction, carbon assimilation reaction. That is atmospheric carbon dioxide you have to reduce for the carbon generation of carbon fuels. Carbon dioxide can be reduced to carbon monoxide, to methanol, to methane, and so on. One single carbon product or dicarbon product. So people are now designing molecules to generate that carbon dioxide reductive system and CO2 reduction. Say CO2 reduction leads to this zinc complex shows the CO2 reduction, and that is being studied by different electrochemical technique, and then the carbon dioxide reduction is proved by this GC mass. That means it is methanol that is proved. And also we have several other product. You see, this is another one. This compound, this is also a copper compound. This is copper compound. There are, see, this is a predyl C base, and see this is 1,4-benzene dicarboxylic acid. It forms a copper complex. That copper complex exhibits interesting Knoevenagel reactions. Carbon-carbon coupling, carbon-oxygen coupling, all these coupling reactions are being carried out. We have carried out all these coupling reactions in different solvents, and you see the yield is maximum in this ratio 10 mole percent water methanol solution. Water methanol, which is more green. It is water is full green, while water methanol is relatively green, other than only methanol or only THF, etc. So it shows the highest transformation with 10 mole percent. So this molecule, that is coordination polymer, that coordination polymer is useful in the catalysis. Now I am going to finish my talk quickly. This is an interesting molecule which is isoniazid. Isoniazid itself is a drug. It is used for the TB treatment. For TB drug, it is TB drug, but it has the bridging capacity. So you prepare cadmium complex with this isoniazid molecule, and this cadmium complex is impregnated in a polymer bed, PVDF, polyvinyl system polymer bed, and then observe the piezoelectricity. And we observe the piezoelectricity, only just pressing it, the electricity generates. And this is being used to measure your pulse rate. This pulse rate is measured, so the material is so sensitive that it measures the polymer is just coated on this part, and then its electric change is observed in the signal system. Where your doctor is he is in a chamber at 100 kilometers away from you. Just one sensor is here, so he can easily measure your pulse rate as well as pressure and other informations. So these systems can be very useful as the medical management system. Okay, so superconductivity is one thing. I am going to give you another example of superconductor. This is one copper mop, and which shows the supercapacitor, and because of its you see these nanostructures have huge number of peaks, large number of peaks, and these peaks are responsible for the very high capacitor activity. That's why they are showing the very high capacitor, and the supercapacitor being observed by this galvanostatic charge discharge system. This is the GCD measurement, this is CV measurement. Okay, this is some application part of the metal organic framework, and so on. So I am finished. I mean to say, we are going to design the materials. I told you materials, they are also chemicals. Those have some application potential. They should be stable, thermally stable, optically stable, magnetically stable. Besides, stable in the pH, and they should have the multiple activity. Not only one target is not sufficient today. তোমার বাচ্চা সে যেন ভালো খেলোয়াড় হয়, ভালো ছবি আঁকতে পারে, ভালো সাঁতার কাটতে পারে, ভালো সাইকেল করতে পারে, আবার পরীক্ষায় ফার্স্টও হয়, তবেই সে মাল্টিপল ক্যারেক্টার। ফলে আমাদের মেটেরিয়াল বা মলিকুল যেটা ওরকম, দ্য molecules could have the multiple activity, then it can be useful in sustainable development. I am now the Secretary of Indian Photobiology Society. Photobiology research in country started long back during the time of J.C. Bose. As you know, the J.C. Bose himself was a photophysicist. applied and biology both. And K.K. Rohatgi Mukherjee, illustrious professor of Jadavpur University, Krishna Kamini Rohatgi Mukherjee, she started this Photobiology Society in 1964. And this Photobiology Society is a organization and interdisciplinary to its character, since it includes physics, biology, chemistry, pharmacy, medicine and engineering. And its committee also constituted like the people from the different specialization. And in our country, photo research, photochemical research, photo research in photochemistry started by this person. He is N.R. Dhar, Nil Ratan Dhar, a student of Acharya Prafullo Chandra Rai, who was the torch bearer of chemistry in northern part of the country. Allahabad University is founded by this man, who was the founder, professor of Allahabad University Chemistry Department. If you go Allahabad University, then in the chemistry department you will find his cutout. He was the father of physical chemistry. And he, noted as the father of physical chemistry, his illustrious students, noted students R.C. Mehratra. Mehratra is well known to the Educational Commission of Government of India, R.C. Mehratra Commission. ভারতবর্ষের শিক্ষা মানচিত্রে মেহরাত্রা কমিশন একটা বিখ্যাত। And also Hiralal Nigam, H.L. Nigam, another scientist, chemist. And then S.S. Bhatnagar, J.C. Ghosh, who was the founder, director of first IIT in the country, Kharagpur IIT. দেখবে খড়গপুর IIT গেটে ঢুকলেই দেখতে পাবে J.C. Ghosh's statue. And he is well known by organic chemist, and he is also a photobiologist. He is Baba Kartar Singh, not so popular, but he was a famous photochemist, organic chemist. Baba Kartar Singh in Lahore University, Punjab Lahore University. M.B. George, Mihir Choudhury, Kangan Bhattacharya. They are the legacy continued. And photobiology science is not now confined in the chemistry only, it is encompassing every other organization. So this photobiology research, I just welcome you to come to KIIT, Bhubaneswar, KIT. In KIT, Photobiology Society is going to organize its annual convention in November 18 to 20. If you go to our website of Indian Photobiology Society, you can find that all sorts of advertisement. I will also send to your teachers about the advertisement you join with, and the funding agency like CSIR, DST, as well as UGC and my university, all they supported me, and some of my group members and the students, those have contributed to me for this reaction, for this type of achievement are they. And this is the Photobiology Society program, some flyer I will send you all. So thank you sir, thank you giving me this chance to give some essence of my talk. And if you have any query, you can ask, or you can see the
Student, any question? Is there any question?
ও নেই এখন
Sir, nahi.
হ্যাঁ কোশ্চেন আর নেই, সব বুঝে ফেলেছে। ঠিক আছে, ফ্যান্টাস্টিক, থ্যাংক ইউ।
Thank you sir for your nice and informative lecture. Please.
Thank you very much to our esteemed guests for this wonderful session. Now we will begin the oral presentation.
Participants are Orko Patra, research scholar from Jadavpur University, Shantu Bishoy, Research Scholar from IIT Kharagpur, Shuman Bhatta, Research Scholar from IIT Kharagpur, Putul Karan, Research Scholar from Midnapur City College. We would like to invite Mr. Orko Patro first to come up on the stage for his presentation. You have 10 minutes to present.
Good afternoon, everybody. Myself, Orko Patro. I am doing research under Professor Chitranjan Sinha in Jadavpur University. I am going to deliver a talk on the topic entitled as Manitz-based capped fluorobees tetranuclear nipple to defective dicuban core type complex, its structural analysis, catalytic oxidase activities, magnetism, and electrochemical studies. My lecture will be based on the following points. Introduction, the design of the newly synthesized manitz-based ligands and its different coordination modes, the scheme of synthesis of the tetranuclear nickel complex and its characterization through the help of different spectroscopic techniques. The application will be based on the catalysis, electrochemistry, and magnetism. So there are two different types of ligands that we can synthesize for the formation of different types of metal complexes. Maximum of those ligands can be based on either SIB base or manitz base. So here is the three different structural aspects of manitz base. Actually, I will go to the next slide. Yeah. So SIB base, as you all know, that it can be a condensation product of aldehyde or ketone with an amine. Now that amine is mainly primary amine, so that the water molecule can be opted out in the product. So the main aspect of the SIB base is it is useful for the formation of mainly mononuclear or in some cases dinuclear metal complexes. But for manitz base, if we design the manitz base with a beautiful idea, it can be useful for the formation of, you can see the multinuclear, it can be dinuclear, it can be trinuclear, tetranuclear, even hexanuclear, depending upon the metal ion concentration. So the polynuclearity comes into the picture when it is about the manitz base. But that is not the case with the SIB base, because in the SIB base, you have a limited number of donor atoms, and those are in very close proximity. That's why they are able to form mononuclear, mainly mononuclear metal complexes. Here are some of the examples of dinuclear copper is missing somehow. Okay. Yeah, in this. Okay, some of the copper atoms are missing here. In these two holes, there are two copper atoms. So it is basically a dinuclear copper complex. And the next example, you can see there are three cobalt atoms. So it is a trinuclear cobalt complex. So these are some of the examples that you can form using the help of manitz-based ligand. So this is the following ligand that we have synthesized in the laboratory. As you can see that there are total 6 number of donor atoms, 2 nitrogen and there are 4 oxygen atoms. So if you combine all those donor atoms, you can be able to create 2 types of pocket. Now what does that pocket mean? Pocket mean is kind of a cavity in which you can be able to incorporate the metal atom, right? And depending upon the nature of the metal atom, you can form either homonuclear or heteronuclear metal complexes. For example, here are some of the coordination modes. You can incorporate 3D, 4D or even lanthanides also. So if all in the multinuclear system, if all the metal atoms are same, then those are called homonuclear complexes. Or if there are 2 different kinds of metal atom present, then it will be named as heteronuclear. So the first pocket generally used for the incorporation of 3D transition metal atoms, where the second pocket can be available for larger size metals. The ligand has been characterized with the help of 1H NMR, IR as well as the mass spectroscopy. Here the single peak indicates the bulk phase purity of the ligand. Okay. The ligand has been further characterized with the help of single crystal XRD technique, where you can see that there are 2 oxygen atoms that are available. Actually hydrogen atom has been eliminated for the clarity of the ligand. So these 2 oxygen atoms can be deprotonated easily with the help of trimethylamine or any other base, so that they can be directly involved in the binding with the metal. And there are other 2 neutral oxygen atoms and neutral nitrogen atoms present in the moiety. Okay, the bond angle and bond length has been given here. Okay, so with the help of this ligand and we have been chosen nickel metal, we have been able to synthesize this tetranuclear complex, nickel complex, where there are 4 different binding scenario. You can see the nickel 1 and nickel 2, these 2 are in kind of similar environment, whereas nickel 3 and nickel 4 are also in the similar environment. But these 2, nickel 3 and nickel 4, has been connected together with a doubly breached fluoride ions, whereas the nickel 1 and nickel 2 has been directly attached with the ligand. And it is in centrosymmetric in nature. Okay. The metal complex has been also further characterized with the help of mass, IR and UV spectrum. Here also we can see that the complex, when you dissolve a complex in any kind of solvent, it may form a mononuclear part. We have been able to trap this mononuclear part in the mass spectroscopy as we have got a single peak. Okay. So we have been focusing on mainly 2 or 3 kinds of application. The main is catalytic oxidative activities. So we have been chosen 2 different substrates. One is catechol, another is 2-aminophenol. So here what he did, we take the UV spectra of the substrate differently and also the complex, and then we mixed both of them together, and we did a UV measurement with a time span of 3 minutes interval. And we have been able to show that the spectrum at a wavelength around 410 nanometer has been increasing with respect to time. And that is due to the formation of quinone band that is shown in the here. That is due to the formation of quinone band with time. That means our molecule is able to catalyze the catechol into its corresponding quinone derivative. The corresponding rate calculation plot, that is the line Weber bar plot, has been given here. Okay. Now coming to the mechanistic pathway. So about the tetranuclear or any multinuclear complex, all the metal atoms cannot be involved in the catalytic activity. Some of them can be more active than the other 2. So here what happened, if you see the structure, this nickel 1 and nickel 2, these are with the direct attachment with the ligand, whereas nickel 3 and nickel 4 are being breached with the chloride atoms. So this nickel 1 and nickel 2 are more active than the nickel 3 and nickel 4. So if they have to show any catalytic activity, this nickel 1 and nickel 2 has to be free. That's why when we dissolve the complex, we first got this mononuclear part where the nickel atom has been attached with one with water molecule, another one with methanol molecule to fulfill its octahedral coordination mode. So when we put the catechol into the solution, it first binds with the catechol with these two different modes and finally comes down to the C intermediate. Then the nickel 2 got reduced to nickel 1 with the formation of an organic radical. And this radical formation can be confirmed by taking an EPR spectra, where this spectra, the EPR spectra, this spectra actually confirms the presence of an organic radical here. And then the corresponding, this moiety gives back to quinone derivative along with the formation of an square planar nickel path, which again combines or dissolves in the water and methanol solvent mixture to give back to the original moiety. Also, we got a byproduct, that is hydrogen peroxide. So when doing the oxidation part, we separated the aqueous mixture in which the H2O formation was going on, and that was, we did an UV spectra where the formation of H2O2 and I3 minus, we got that mixture around a 353 nanometer. And the mass spectrometric analysis has been done for the intermediates. This is also phenoxygen synthesis-like activities where the molecule has been able to catalyze orthoaminophenol into the corresponding phenoxygen moiety. The corresponding rate calculation step has been given here. This is the corresponding mechanism where the same mechanistic pathway is going on, where the nickel 2 at the end of the scenario is getting reduced to nickel 1, and same organic radical has been formed. The corresponding complex substrate intermediate formation has been confirmed by the presence of mass spectrometric analysis. We also did the magnetic susceptibility measurement, where the magnetic susceptibility at the room temperature is found to be 5.2, which is the close value for the nickel 2. And actually the main characteristic is about the ferromagnetic nickel-nickel interaction, which got confirmed by the value of magnetic susceptibility, which gets increases around the temperature decrease, and due to the presence of predominant ferromagnetic nickel-nickel interaction. Actually, two types of different nickel-nickel interaction has been found, that is J1 and J2, that is shown here. J1 is due to the single oxido bridge, and J2 is given due to the presence of the doubly chlorido bridge. We have been able to show the oxygen evolution reaction and hydrogen evolution reaction. So these are the plots for the OER study. We can see, I will go through directly, these TAFL plots. The TAFL plots, the lower TAFL slope value of the 121, that is for the complex 1, shows a better OER kinetics than the corresponding glassy carbon that we have taken as a reference. And this is the picture of the bubble formation during the process. Also, here the small semicircle that interferes or that gives us an indication of the slower value of the overpotential, and also the solution, charge transfer resistance value that is given here around 130 ohm. So these two things confirms that the complex is able to show a better OER activity than the corresponding glassy carbon electrode. The stability of the complex around that particular electrode potential has been shown in the plot E. Okay, and this is the study of the HER, that is, it is showing intermediate HER activity with respect to the platinum as well as the glassy carbon electrode, because the platinum is able to show a better very lower overpotential with respect to the complex 1. And also here the two types of different resistance we got, that is, one is the solution resistance, another one is the charge transfer resistance, that is given here, the values are given here. Charge transfer resistance is around 71 and the solution resistance is around 43 ohm. Also we did the same stability formation curve, that is, our complex is able to be stable for the around 3 hours in that particular charge potential. And formation of the hydrogen gas has been also shown here in the picture. So these are the three applications that we have been focusing on. So two types of catalytic activity, the magnetic measurement as well as the HCR as well as the OAR study. And I have taken these references for this project. And I would like to thank my supervisor, Professor Chitranjan Sinha, and my funding agencies, CSR India, and also my dear lab mates for this wonderful work. Thank you.
Any question? কেউ question করতে চাই? Okay. নেক্সট হচ্ছে শান্তনু বিষয় আইআইটি কেজিপি নাকি সন্তু আছে এটা আচ্ছা সন্তু বিষয় আইআইটি কেজিপি
শো করছে না ওইটা হ্যাঁ ওইটা ওই কনফারেন্স প্রথমেরটা হ্যাঁ ঠিক আছে নিচেরটা টান নিচেরটা চেঞ্জ হচ্ছে না সাইড চেঞ্জ হচ্ছে না Good afternoon everyone. I will discuss my research work entitled as Synthetic Studies to a Naturally Occurring Neurohybrid A under the expert guidance of Professor Somik Nando, Department of Chemistry, IIT Kharagpur. So this is the contents of my presentation, and the neurohybrid A is belongs to the family of merotarpine, and this molecule gain our attention due to its complexity, and it processes a C15 carbon skeleton, and having the C15H16O4 this molecular formula, and this presence of this gamma electron moiety, and with this methyl and vinyl fragment at the beta position, and this is connected via sp3 bridge methyl with this benzoyl group, and this too much interesting towards the due to its application to medicinal chemistry and therapeutic index, and this molecule was isolated from the leaves of the Hypericum Chinese along with this merohybrid B and this merohybrid C, and it is optically active, colorless gum, and it has several activity like antioxidant activity, and it can be used as antioxidant supplement food, and this neuroprotective effects, and this effect requires further experimentation. It shows the antimicrobial activity, anti-inflammatory properties, and it can act towards very cancer-like cell, and shows this anti-cancer potential, and its congeners hyperlactone A shows the anti-HIV activity. So we can also expect that these or molecule have similar type of activity can show. So this is the retrosynthetic design, and this is the three main disconnections are electronization, oxidation, and this hydroxylation. And now our aim is to design the efficient synthetic route. For that purpose we choose our starting material, diethyl malonate. This is very really available in the market and is low cost efficient, and now it is treated this diethyl malonate with sodium hydrate base and reacted with allyl bromide. We formed this compound 2, then compound 2 is further reacted with lithium aluminum hydride. We got this compound 3, and compound 3 under this mono alcohol protection, and this is a very controlled experiment because there is a chances of 2 alcohol group might protected, and that's why several TLC monitoring is required. And after this compound 4 in our hand, as this is a enantiomeric compound, so there is two mixture, and we try to fix the stereocenter of this quaternary center, and for this purpose we use this lipase based enzyme, Candida antarctica lipase, and and for two enantiomer, one is react faster, that convert to acetate, and another is react very slowly, and once the reaction is 1:1 ratio, we stop the reaction, and this compound 6 having our desired chemistry stereocenter, and we move forward with this compound 6, and compound 6 underwent this TBTPS protection followed by ozonolysis. We got compound 8, and compound 8 under Pinnick condition from this acid compound 9, and compound 9 with reacted with DBU and ethyl iodide, we got this compound 10, and this compound 10 further react with TBF to form this initially TBTPS group was deprotected, and then in one pot it formed the cyclogist product compound 11, and now this compound 11 is treated with this LHMDS base, and it reacted with alpha methylenestyrene derivative from this alkylated product compound 12, and then now compound 12 further underwent this Davies oxidation for the installation of this alpha hydroxy group at that position, and for this there is two types of Davies oxidation catalyst, one is plus, another is minus, and our case this Davies oxidation reaction, we use this plus isomer, and once this compound in our hand, we perform this ozonolysis reaction, and then we got this compound 14, and this compound 14 require further optimization to got our target material molecule compound 17, and from this we can say that this is the molecule, natural product merohypyrin A. This is the fast synthesis, and we fix all the quaternary carbon center through enzymatic kinetic resolution. We can say it is enzymatic enantiomer selective desymmetrization, and we construct all the quaternary C4 stereocenters by the exploration of the rastroselective enolate alkylation, and the present study aims to develop this application of this Davies oxidation, and its efficiency is a valuable method for the installation of the alpha hydroxy group, and our objective is to support the advancement of the merohypyrin A for the promising its therapeutic agent and primary compound for subsequent investigation in medicinal chemistry. And from that we, although our focus is to synthesize our natural product merohypyrin A, but we can also understand that how the knowledge of the retrosynthesis and to how we easily design a target molecule planning, we also understand from this. And this is the future plan, and once this compound is in 14 in your hand, then we have to deprotect this PMB by using the ferric ammonium nitrate or DDQ. We got this then oxidation followed by VT reaction, we got our compound 17. And now I would like to thank IIT Kharagpur for providing all the research facilities and funding agencies, and Midnapur City College for providing this platform. And finally, thank you for all of you for your kind attention.
Any question from the participants? Is there any question? ঠিক আছে, okay. Next, Sumon, IIT KG.
Good afternoon everyone. Today I am going to present my research work, synthesis of acridins by anionic benzanulation strategy, and under the supervision of Professor Somik Nanda, Department of Chemistry, IIT Kharagpur. Today I will cover the following topics: introduction, synthetic application of acridins, our strategy for acridin synthesis, screening of reaction condition, and proposed reaction mechanistic pathway, experimental data, and synthetic utility and few post-functional synthetic functional modification, concluding remarks, and future direction. Acridins are nitrogen containing tricyclic scaffold like that of anthracene, where one CH group is replaced by nitrogen atom, and in 10 position acridins attracted considerable interest towards synthetic community due to its novel planar tricyclic structure and broad range of biological activity. In 1870, Carl Grave and Henry Caro first isolated acridin from coal tar. Applications of acridins are used as antibacterial drugs, such as 9-aminoacridin, also used as antibacterial, antifungal, and anti-leukomyotic, and antiviral. More recently, it also used in industry as pigments and dyes for long times, and more recently it used as a organic photocatalyst for the organic synthesis. Our proposed strategy towards synthesis of acridin derivatives. We thought that if we prepare quinoline derivative, and if we could generate carbanion alpha to this 2,3 disubstituted quinoline, and this carbanion could attack the various Michael acceptor in beta position, followed by cyclization and Dieckmann condensation to produce our required acridin derivative 1-hydroxyacridin or 4-hydroxyacridins. For that purpose, to prepare our required starting material quinoline derivative 6, we used easily available starting material orthonitrophenylaldehyde as our starting material, and when it reacts with methyl or ethyl acetoacetate in presence of zinc chloride and stannous chloride in ethanol or methanol solvent, it produces quinoline derivative 3. Quinoline derivative 3 on benzylic bromination produce quinoline derivative 4. Quinoline derivative 4 treated with thiophenol and triethylamine in chloroform solvent produce quinoline derivative 5. Quinoline derivative 5 on oxidation with sodium periodate in presence of methanol water 7:1 ratio to produce quinoline sulfoxide 6, which is our required starting material. Screening of having quinoline derivative 6A in our hand, we started our journey to screen our optimized reaction condition. For that purpose, we used methyl acrylate as a standard Michael acceptor, and here we used various bases, and in different solvent we used inorganic bases like cesium carbonate, potassium tertiary butoxide, and also organic bases LDA, LHMDS, lithium tertiary inorganic bases lithium tertiary butoxide, sodium hydride. Different bases we used, but we got our desired product when we used LHMDS organic base in THF in -78 to 25 degrees centigrade. This is the proposed reaction mechanistic pathway based on previous reports and literature. Here LHMDS abstracts the alpha hydrogen of SOPH group, and this generates carbanion, and this carbanion attacks beta position of this ester in a Michael addition fashion to produce the another carbanion alpha to this ester group, and this carbanion then attacks the ester group followed by cyclization and thermal olefination and aromatization to produce our desired acridin derivative 8. For there are many unsaturated esters are used, all are not easily available, so we prepare unsaturated esters by using traditional Horner-Wittig reaction pathway, and here we prepare different types of unsaturated ester and beta aryl and beta aryl and also beta heteroaryl unsaturated esters also produced, and this is having quinoline sulfoxide 6 in hand and having optimized condition in our hand. Then we move to forward the synthesis of different types of acridin derivative by using different types of unsaturated esters. We got very good to excellent yield when we used methyl acrylate, ethyl acrylate, and also this reaction are well tolerated when we used methyl and ethyl group in beta position of ester. And interestingly, when dimethyl malate, where two electron withdrawing group are present, then we got our desired product with excellent yield, 81% yield. But when this beta position becomes bulkier, then we got a trace amount of product. Unfortunately, we did not got any product when we used vinyl sulfone as a Michael acceptor. Here also various types of beta aryl and beta hetero aryl functional group are present in unsaturated ester, and we got good to excellent yield. Next, when we substitute, we take the bromine derivative of 6A, and we used our common Michael acceptor, we got our desired product, a good to excellent yield. This is the 1H NMR spectrum of our compound 8A in D6-DMSO, and this is 13C NMR of our compound 8A in D6-DMSO. And we then having different quinoline acridine derivatives in our hands, we then started to use these derivatives for post-synthetic modification, and for that purpose compound 8B under triplication in presence of triplylic anhydride in triethylamine and DCM produce this triplet derivative of acridine, and then it delivered the compound 9B in a one-pot reaction when in Suzuki condition in presence of phenyl boronic acid and palladium catalyst. And compound 8J also converted to its 9J derivative by using DAPCO and methyl propiolate in dry DCM condition. Compound 8R, we obtained a 9R acridine derivative compound from compound 8R via using the standard Suzuki reaction condition in presence of phenyl boronic acid and palladium catalyst in presence of dioxane water 3:1 ratio at 110 degree centigrade. We converted compound 8W under traditional Stille coupling pathway by using tributyl allyl trin and in presence of palladium catalyst at 110 degree centigrade in toluene to our desired 9W product. So we developed an efficient and synthetic strategy for the synthesis of highly dense regioselective acridine derivatives starting from orthonitrophenylaldehyde, and we used anionic 4+2 benzaldehyde strategy, and our strategy also mild and straightforward method, and which are not reported till date. And we exploration of the development methodology to the synthesis of natural occurring acridines. We also use transition metal free strategy. This is our future plan. We can use the traditional von Leusen strategy for the synthesis of the spiral moieties, and this after various functional group transformation, if we could generate this pyrrole moiety derivative like here the sulfoxide group are present, and if we could generate the carbon ion here, and again anionic benzaldehyde strategy is applied, we can produce isoenol derivative, another heterocyclic moiety. I would like to thank my supervisor Professor Somik Nanda for his constant guide and support, and also IIT Kharagpur to give me the platform and opportunity, and also Midnapur City College to give me this opportunity, and thank you all of you.
afternoon, respected sir and ma'am and researchers and my students. I am Putul Karan. I am working as a research scholar in Midnapur City College under the guidance of Dr. Abhishek Ghosh. Today I am going to present my research work entitled Synthesis of Novel Bioactive Azokumarin Derivative, Cytotoxicity, DNA binding, BSA binding and their in silico analysis. Now we come to the first slide, introduction. As we all know, coumarin, which is a oxygen-based heterocyclic compound, which have widely used in pharmaceutical industry. Most of the natural and synthetic coumarin and coumarin derivative have shown various biological activities such as antifungal, anti-cancer, anticoagulation, etc. This slide shows some biological active coumarin derivative. My aims and objective of my work is synthesis of novel biological active azokumarin derivative in aqueous medium, spectroscopic characterization of the synthesized compounds, geometry optimization and frontier molecular orbital analysis of the synthesized compounds, evaluation of cytotoxicity, DNA binding and BSA binding efficiency of the synthesized compound, and in silico analysis of the synthesized compounds against BSA and DNA to identify the binding ability and binding site in DNA and BSA. I synthesized a novel azokumarin derivative using the diazocoupling reaction of thiaminopyridine with coumarin. The compound is, this is the novel compound 6-pyridyl azokumarin, and after synthesis the compound is characterized by IR, proton NMR and 13 NMR and HRMS mass spectroscopy. Next, successfully characterization of the compound, I carried out DFT calculation of coumarin and 6-pyridyl azokumarin to explain the reactivity of the synthesized compound. From this slide we can see that the energy gap of the synthesized compound is decreases, the homonomy energy gap is decreases, so we can see that we can conclude that the synthesized compound is chemically and biologically more reactive than coumarin. As the compound is biologically active, so I carried out the MTK-SS study to evaluate the cytotoxicity of the compound. From this slide we can see that in low concentration our synthesized compound is in low concentration 2 micromolar dose, our synthesized compound is more active than coumarin. This black is shown coumarin, and with the IC50 value of 6-pyridyl azokumarin is 9.09 and IC50 value for coumarin is 9.9. So the compound is more cytotoxic. As the compound shows cytotoxicity, so we carried out the DNA binding interaction with the 6-pyridyl azokumarin, and the binding constant of 10 is 1.64804 into 10⁴ mole inverse. To confirm the binding mode with the DNA, I carried out ethylium bromide displacement studies and Daphne displacement experiment. Here no displacement of ethylium bromide occurs, so interaction not occur. That means intercalative type of binding is not occur. So I carried out the Daphne displacement experiment, and here we can see that the fluorescence intensity is coins for both of the two compounds, but in case of our synthesized compound the intensity is more decreases, so the compound is the binding mode of the compound is group binding. And next I carried out to confirm the binding site of DNA, molecular docking study is carried out, and this slide shows the binding mode of ctDNA with 6-pyridyl azokumarin, and these are the binding interactions. Next, I carried out the BSA binding studies with using UV visible spectroscopy, and the binding constant of 10 for coumarin is 1.64 into 10⁴ mole inverse, and for our synthesized compound is 3.83 into 10⁴ mole inverse, which is much higher than the coumarin. Next, I carried out BSA binding studies by fluorescence spectroscopy, and to know about the microenvironment of BSA, I carried out synchronous spectroscopy, and from this It is the spectrum of for delta lambda 60 nanometer, and from this the 2 nanometer is shifted fluorescence intensity. So the micro, after binding with BSA protein, the microenvironment of tryptophan residue of BSA protein is changed. And 3D fluorescence spectroscopy also carried out, and we can see that after binding with compound, the intensity of this is decreased. And next, time result fluorescence decay studies is carried out to confirm the reaction is static type of binding or dynamic. And from this we see that the decrease in the intensity is not marked, so the binding type is static. And also isothermal titration calorimetry of 60-viral azocoumarine with ctDNA and VSA is carried out to evaluate the total thermodynamic parameter of the compound. And this table shows the thermodynamic parameters. The delta H value is positive for 60-viral azocoumarine ctDNA complex. That means the reaction is endothermic, and for VSA the reaction is exothermic. And to confirm the BSA binding site, molecular docking also carried out in the PDB code CV03. And next part is conclusion. The present work demonstrates the successful aqueous-based synthesis of 60-viral azocoumarine using coumarine and triaminopyridine, and the compound is successfully characterized. Cytotoxicity study on human brain glioblastoma cell line LN229 shows the synthesized compound is more effective than in comparison to coumarine itself, and UV visible and fluorescence spectroscopy is used to investigate the interaction of 60-viral azocoumarine and coumarine with DNA and BSA. The BSA binding experiment also confirmed that 60-viral azocoumarine forms a more stable complex with BSA. In silico analysis further confirmed the binding of 60-viral azocoumarine with BSA and DNA stronger than that of coumarine. I would like to express my sincere gratitude to the Honorable Director Sir of Midnapur City College, Dr. Pradeep Ghosh, for providing me research facilities. I thank my supervisor, Dr. Abhishek Ghosh, for his continuous support and guidance. I also thank Dr. Sudipta Chakraborty, Midnapur City College, as collaborator. I am thankful to Dr. Sanjeev Kumar Patra, IIT Kharagpur, as collaborator. I am thankful to Professor Saurabh Chatterjee, NIT Raulkela, as collaborator. I am thankful to Dr. Moidul Hossain, Vidyasagar University, as collaborator. I am also thankful to Dr. Jagannath Pal, Midnapur City College, as collaborator. I am also thankful to Dr. Sudip Chandra Pal for helping me in data analysis and manuscript writing. Thank you.
Thank to all the research scholars for the oral presentations. As we have come to end of our oral presentations, we will move to poster presentation. After that, the valedictory session will start.
স্যার বলুন স্যার বলুন We have returned after the poster presentation. Now it's time for the valedictory session. We would like to honor the students who have held some position first, second, third in the poster presentation. First position goes to Sushmita Sheth and Sonak Vishwas. I would like to request Principal Sir to honor the students. Second position goes to Karlul Das, AKMD Azizul Haq, Utpal Pramanik, Shatadru Giri Goswami. I would like to request Moidul Sir to honor the students. Principal Sir to honor the students. Third position goes to Stuti Bhattacharya, Shongita Pati. I would like to request Principal Sir to honor them. Next, award for the poster presentation of the research scholars. First position goes to Samarish Paria. I would like to request Moidul Sir to please honor the students. Second position goes to Shontu Bhunia. And third position goes to Shubhecha Shabud. Next, awards for the oral presentation of the research scholar. The first position goes to Putul Karan. I would like to request Shamili ma'am to please honor the students. Second position goes to Shantu Bishoy, IIT Kharagpur, from IIT Kharagpur. And the third position goes to Orko Patro from Jadavpur University. Now we have reached the end of our conference. It has been 2 very significant days for our college. I would like to request the organizing secretary of this conference, Dr. Abhishek Ghosh sir, to end this day with the speech.
Hello. Good evening, everyone. Today, I feel incredibly honored and privileged to have been allowed to extend a vote of thanks on this auspicious occasion. On behalf of our college whole fraternity, I sincerely thank the guests of honor and speakers for taking time from their busy schedule and gracing the occasion with their warm presence. It is indeed a great honor for our college to have welcomed such prominent speakers known for their great contribution to their respective research fields. After the successful completion of this premier event, I would like to express our sincere gratitude to the Honorable Director Sir for his immense support for organizing this conference and CSIR who give us fund. I would like to thank Principal Sir Dr. Sudipto Chakraborty to encourage us to conduct this event. I would like to thank our Vice Principal Dr. Kuntal Ghosh to support us to organize the conference. On behalf of our college whole fraternity, I sincerely thank the guest of honor, Professor Amit Basak, Professor Chittaranjan Sinha, Professor Brajagopal Bagh, Professor Devashish Ray, Professor Saurabh Chatterjee, Professor Moidul Hossain for taking time from their busy schedule and gracing the occasion with their warm presence. It is indeed a great honor for our college to have welcomed such prominent speakers known for their great contribution to their respective research field. Now, I would like to thank our Assistant Registrar, Mr. Abhishek Das, for his immense support to conduct this event. I would like to thank Mr. Suman Mollik to do all the computer-based work. Without him, it was very difficult for us to organize this program. I would also like to thank our office staff, Momita Madam and Haru Patro, to support us to organize this program. I would like to thank our all library staff and especially Mr. Ashish Barik to publish our conference proceeding paper. Last but not least, I want to extend a vote of thanks to our organizing team, Dr. Jagannath Pal, Dr. Monisha Das, Dr. Prankrishna Manna, Mr. Shubhamoy Das, Mr. Biswajit Mollik, Dr. Atanu Das, Mr. Obhi Kole, and our research scholar, volunteers, and students for making this event happen so beautiful. They gave their precious time and hard work dedicatedly for this conference. I now close my speech and wish everyone success and good health. Thank you.